I don't need to provide too many words of introduction to our session 3. We will be, in a sense, repeating the similar format. You can see our stellar afternoon lineup, but I've indicated along the way that we are grateful to any number of sponsors and partners, and one of them, not just for this symposium, but really to the on-campus constructions, has been Binderholz, which, as many know, is one of the world's leading manufacturers of wood products. So Justin Harries is here to represent Binderholz. And Justin, would you want to say just a few words of greeting to everyone?
I would.
So thank you, Justin, and thank you, Binderholz. A round of applause, please. So again, we will have two presentations, a short coffee, a rest break, and then two further presentations, one more panel discussion, and then a reception as a further reward for a day's work. And it is productive work altogether. Thomas Robinson, Jeremy Smith, Kelly Harrison, Erin Dorf, in that order. And let's begin. Thomas Robinson of Lever Architecture is the founder and principal of Lever Architecture in Portland, Oregon. His practice is dedicated to the creation of buildings and spaces that elevate human experience, as well as pioneering the use of cross-laminated timber in the United States. Lever Architecture has been recognized with numerous awards, including being named to Architecture Records Design Vanguard and the Architectural League of New York's Emerging Voices. The firm's work has been published in The Atlantic, The New York Times, Surface, and Dwell, and was recently featured in Timber City, an exhibition at the National Building Museum in Washington, D.C. Prior to establishing the firm, Thomas led cultural and institutional projects for Allied Works and Herzog & de Meuron. He is a graduate of the University of California, Berkeley, and the Harvard GSD. Thomas Robinson.
Thank you, Peter. It's really an honor to be here. I remember a dinner with Steve and Melissa about a year ago where I was saying, I feel like there needs to be more discussion about design and timber. And lo and behold, Steve said, I just had that discussion with Peter. and you know, some of the ideas behind this conference today were born, and Steve's obviously stepped up with the many other sponsors, and I want to give Peter all the credit for making this happen, as well as the, you know, the faculty and staff here at the University of Arkansas. I have a little bit of a different talk today, because you know, which is really about what we've been doing maybe in the last couple years, and I've titled it Mixed Materials Hybrid Mass Timber. And what does that mean? Hybrid, you know, if you go into Google and you find out, when you Google hybrid, guess what comes up? It's a Prius. And it made me think about this idea of like, what is a Prius? It's actually probably the most revolutionary car after the Model T. There's been 4.4 million Priuses sold, and it's a little engine and a big battery. And they work together to get you from A to B. And I think that at this point in maybe where we're talking, at least in the United States, so it's a different kind of environment, I think we might be in the Prius stage of mass timber, and hopefully we're going to get to the, you know, fully electric car stage down the road. But as somebody who's sort of gone in with like, okay, I'm going to make it all out of wood, it's going to be amazing, as you hit the market and the reality of projects, it's just a little different out there. And I think from our kind of point of view, I mean, we're based in Portland, Oregon, and I've been there 16 years now. For us, everything sort of starts in the landscape and the forests. And that connection to the forest is something, and that sort of sublime landscape of the West is sort of where we draw our inspiration. I think there was some discussion earlier about the amount of forest that you have in a particular landscape. And in Oregon, we have, I think it's 30 million acres of forest. There's 63 million acres in Oregon, so we're about 50% forest. Compare that to Arkansas, where there's like 34 million acres in Arkansas. So just to give you a sense of scale and how the forest defines our landscape and how it's so much part of our culture, how it's so almost every politician in the Oregon State House comes from a timber family. So it's really part of the culture. And one of the things that we got involved in this, we felt like there was this amazing resource right under our nose, and so we got I personally was really interested in the whole process, and we kind of coined this term, forest to frame, that you almost have to, if you're going to change things, you almost have to start from kind of each step and work your way back to the forest. And also, whenever I talk about architecture in the United States, I think it's important to talk about building culture, because I worked in Europe for a while. I wanted to get out of the United States because I'm like, God, I just don't see many buildings that I really want to do here. So I went to Europe, worked there for 3 years, and I came back, and then I sort of started to think about this idea of what is our tradition for building in wood here. And it's very different, and it's really stick frame, and it's been around since the 1830s, and our entire supply chain, everything we do is in a way related to that way of building. And we have almost 200 years of experience doing that type of work, and it defines how we build, the connections we have, the kind of contractors and what they have. And it's really been developing, and just to kind of give it away, and to me, the height of that, the pinnacle of that supply chain and that kind of tradition is Thorncrown Chapel here, in Arkansas. And to me, when I saw that, and it's one of the reasons I wanted to come here, was to really sort of trace that trajectory and then think about what does that mean for the future? What is the traditions that we can bring to architecture, as we move forward? That supply chain is directly connected to my kind of interest in architecture. This is a house that my great-grandfather built in 1928, and that wood for this house came in a boxcar from Bend, Oregon, all the way to Cape Cod, all the way across the country, and then was put together by 2 Irish carpenters who immigrated. So there was a connection to Europe, and you can still see all their fingerprints, on the wood if you look there closely. But that experience, that kind of material experience, is something we wanted to bring to our buildings and to our architecture. It's like a visceral kind of connection that people talk about with wood, and I've kind of left out a lot of the carbon kind of issues. Those are also incredibly important, but I think if you can't make that kind of personal, visceral connection, people aren't going to understand why they're doing what they're doing. This is our office in Portland, Oregon. So this was the first project that we're aware of. It was a spec project. It's a 16,000 square foot building, and it's the first to use domestic, so Oregon-made, cross-laminated timber, grown in Oregon, fabricated in Oregon. And honestly, nobody really knew what they were doing when we did this. And it was great because I saw this picture show up, in your presentation. I was like, wow, I can't believe this picture that I took made its way through the internet. And nobody really knows this, but the panels were hand cut. They were cut with precision German hand tools. That's what they told us, because they didn't have a digital CLT kind of cutter at that time. And so this was like, but it shows you the sort of journey that things have taken. So, but I like that how that has become something that when you Google CLT panels, it comes up, as opposed to when you Google hybrid. So I think that we're really interested in how what we do connects to popular culture, how we can plug into it, and that's why when we call it ourselves lever architecture, it's about the idea of where do you put that lever and how do you actually make a massive difference by intelligently sticking it in the right place. This is one of my favorite images of our building, and basically because everything that we are interested in is there. In the distance, you see Mount Hood, and the range where the wood that you see hanging in the air is 3 hours south on that same range, and then it's basically fabricated then and delivered to our site and then erected by people in, our urbanizing environment of Portland, which is kind of exploding with growth. I mean, myself alone, I'm just a little architecture firm. I have 4 tower cranes in Portland right now. There's more tower cranes in Portland than I think a lot of cities that are much larger, including, I think, Chicago and New York. So I'm going to talk a bit about sort of our early innovation timber and then end with a couple projects. I'm going to cover a lot of ground. This is one of our earliest projects, 2013. It was basically a total spec retail project where we took 2 properties on opposite ends of a street, combined them, and stuck a Parisian-style passage through them. It's kind of a crazy developer project. And as I was driving out to the gorge, I noticed this huge forest, a really weird forest, like everything growing in a line. And I asked some of my friends, who owns this forest? And they're like, oh yeah, it's the Collins family. Yeah, I know them. Yeah, you should talk to them. And I said, well, maybe they'd be interested in supplying all the wood, for the interior of this project, because we knew it probably would be really cheap, just because they usually made it into wine boxes. So this was an FSC certified farm forest, originally planted for biofuel. And we kind of directly contacted Collins. They said, yeah, we'll do that. So then we directly contacted the milling company to mill the wood, and then that's how that all came to be. A selection of other projects. We've done some multifamily. This is I shouldn't say multifamily, this is housing at Oregon Health and Science University. And the reason I show this is this is sort of still our tallest wood building to a degree. It's 85 feet in the back. And like the Thorncrown Chapel, and I'm not going to compare this to Thorncrown Chapel, but technically, it's sort of the pinnacle of what you can do with stick frame. I mean, it's an octagonal structural wood curtain wall with plywood shear walls over 2 floors of PT concrete. So it's about as high as you can go, and we really, just really enjoyed that project. We also do a lot of work for the entertainment company in Los Angeles. You probably didn't know that about us, but that's one of the things we do a lot of, and we work for Walt Disney Company, work for other studios, we work for the Academy, but this was a really important project for us. We were just starting out 10 years ago. This is, I guess, 9 years ago. We got this opportunity to do this project, which is a renovation of a windowless warehouse into a digital animation studio. It's 85,000 square feet. And one of the things we want to do is bring a sense of materiality to the building. And we talked to a wood broker in Portland, and he's like, oh yeah, they're demoing a gym in Redondo Beach. You should check it out. So we took all the wood from that gym, and that's really what we clad, with 10,000 square feet of that wood reclad into this building. We've done some other projects this is a winery that we completed relatively recently in about an hour outside of Portland, and all the wood that you see in the ceiling is the same wood they used for those 5/1 projects that I showed you previously. So it's basically the headers. So all the wood in this ceiling cost $15,000. So it just gives you a sense of like the amount of wood and how it's sort of so direct there. But it's a very different equation in Oregon. So from that, we went to this project, which is another speculative project, which was taking some of the stuff we learned on the winery and, I got it. Applying it to a building that can be divided into sort of 8 different pieces. So that's just sort of the stuff that we worked on maybe 3 years ago. And then there's some more recent project. This is just some more images of our office to give you a sense of what that was. If you're ever in Portland, please come by. We don't get that many visitors, sort of like, so definitely come visit us. And this is sort of this was a completely speculative project that I did for a friend. We didn't even plan to move into this building. And maybe he owed us a little ad service, and so we sort of negotiated something, and so we moved into the top floor of it. And then probably the project most people know us for is Framework, which is one of the winners of the Tall Wood Building Competition. And this was like a complete adventure in, I guess, pure wood. And we, spent literally 2 years. I feel like I'm still sort of recovering from all the work we did on this project, getting this permitted, going and doing the testing, doing this kind of radical, tall post-tension rocking wall system, which I think you're going to hear more about post-tension rocking walls, which is like completely, I'm not going to even talk about it because he's going to actually really show you what's happening. But we did about 40 full-scale tests. We spent about $1 million in testing to kind of do some of the first tests in the United States on, true fully loaded fire testing, acoustic testing, crushing. Whew, I'm getting tired just thinking about it. But it was, we're still involved with a lot of research. I don't know if I can get this to go. Yeah, there we go. So we are still involved in like 3 or 4 sort of research efforts. One of them is testing these rocking walls full scale. So this is a recent, about almost a year and a half ago, test of the rocking wall system. This is the Northridge earthquake, if those of you might know California. But rocking walls are basically, a really interesting, resilient, self-centering design for building. And we're going to be doing, theoretically, a 10-story version of this that we've drawn up, and they're going to be working on that really soon on this same table. So the project that I'm really excited about and want to get into a little more detail is the Adidas North American headquarters. So it's one of these projects that just kind of appeared out of almost nowhere, and we did a quick competition. And we won it. There were 2 buildings that we did here. You can see the building on the right is sort of a larger building, which we call the North Building, and then the smaller building is called the South Building. Sort of organized almost around like a mini stadium around a new pitch, and then reworking the landscape in that area. And what was pretty interesting about this building, and you could see it sort of, this is from about 2 weeks ago. You can see the lower building, it's about 35,000 square feet, and then the upper building's around, I guess it's like almost 400,000 when you include the parking. That's where it was, and you could see that the south building there is almost done. And that's where they have a cafe and fitness center, sort of amenity building, and the main building is their research building. But I think what's particularly interesting about this building is it has a little bit of everything. So you see the existing parking garage there. I don't know if I can. It's fine. You guys can figure it out. And then that little building is sitting on top of an existing parking garage. So we had to actually, do the structure down. And then we built a 5-story below-grade parking garage, and then we have 5 floors on top of that, connecting to the existing parking garage. So Adidas was like, they really wanted to build this thing quickly. So we came up with a bunch of different options. This gives you a little more sense of the 2 plan, and in the process of doing that, we reworked their whole entry, and there was just a huge amount of things that happened. But one of the things they wanted to do was to build it fast. And they also wanted something that related to the brand is this sort of, I think Adidas has just made a huge resurgence in terms of the brand, and part of it is about their sort of authenticity of, how they deal with materials, how they deal with artists, how they, even I see people wearing the kind of retro Adidas stuff. It's like, it all came out of North American headquarters in Portland. And we were sort of thinking, how could we think about this idea of a hybrid structure? Because we went through a bunch of different options. So when we looked at doing this massive parking garage, 600 spaces underground, I'm not super happy about that, but that was the program. We're like, probably not a good idea to do wood underground in a parking garage, but maybe somebody braver than I will take that on in the future. But we thought, okay, well, we can do a precast and plank structure for the parking underground, and then what do we do when we come up? We could actually replace the planks with wood. So we came up with a whole system where we created a perforated post-tension beam, and then created this very simple system with no steel connections where basically the wood just slots into the structure. And this is sort of what you see below grade. Very, very simple, very dumb, huge. And then what we do when we get up top is we switch the sort of system. We create like a perforated precast girder, and then we slot in the CLT. So those CLT, they're 10-foot by 30-foot panels with pre-attached glue lam beams that are pre-screwed to them. They come on a truck, and they just basically pop them into place. It's really interesting. They're going to start putting this up in a week, and they're going to do it bay by bay. So they'll have the precast person do the beams, then they'll come back with the wood. And it's, so that's sort of, it was just, you know, there's a button here that causes things to black out, I know. But, you know, for us, this is sort of as far as we could push them, and we're really excited about the opportunity. It's almost like a cross between, I don't know, parking garage and, I don't know, my grandfather's house. So that to me is sort of where we're at, and I feel like that's sort of, next time we're gonna do something a little different, but we're really excited about, this is the mock-up we did. It's pretty kind of, it's not as tall or as long as any of it, but you get the basic idea of, and one of the things we've learned doing our other buildings and doing framework is like, we wanna make the connection detail as simple as possible to the point where we're almost eliminating the detail. So Dear Johnson, who we've done all our buildings with in Oregon, we love them, they're great, but making it simpler is a good thing. And, you know, and then we can work our way back up into more complexity. So this is just some examples of the kind of character that you'll sort of have. Those beams will be, these will be 30 feet long. So they're big and they match up with the parking. And we're testing out all the pieces. We do these sort of practice buildings where they're literally putting on the facade, they're doing the slab, they're doing all these pieces. And this is sort of the feel of the building. I mean, there was a pair of Adidas shoes where the logo is like it's leather, and then they abrade the leather to make it like almost like rough sawn wood. And that was sort of the idea behind the facade, just a very simple, repeatable panel that we just sort of, almost like we abrade it and flip it, and then you get this sort of quality. And these are some mock-ups of what it will look like. And this is just like a little sort of sun study. I love where it's, the building kind of changes color during the day and changes its perspective as you're sort of walking along it. This is the you know, the south building. It's hard not to love a little building, as people were saying earlier. And we really were thinking more in terms of, you know, this is the existing parking garage, and we put in 2 new transfer beams, and then we came up with the wood, and then a BRB steel frame, sort of a hybrid of steel, you know, and wood, and then, you know, the other building's basically concrete core, concrete girders, and beams, and then the CLT panels. And this one is a very different kind of look. It's almost like a sort of Jenga-inspired structure where we're kind of working with the steel structure, but then sort of crossing it so we can have a place to put the mechanical up high. So this is sort of how that building kind of gets built up. And then just to see it kind of go up here, you can sort of see that steel structure went up in like, I don't know, it was like 4 or 5 days. And then they start to come up with the layers of the wood. And really what, in terms of the detailing for this project, we came up with this really, so this is sort of showing the kind of connection of the BRB frame, which is steel, and then the wood, and we have like one like tendon that holds these wood beams in place. So they sort of see it more in, you know, this kind of gives you the Navisworks model of it, and then this is sort of what it looks like. It's not curving, but you get a sense of the kind of character of it. And one of the things that inspired this was just how do you make the detail as simple as possible? This is, on the right is I was in Japan because my daughter she went to a Japanese immersion school, and we went there for the first time, and I was so struck by not the temples, but the kind of utilitarian buildings and things that support the temples. So this is in Kyoto. This is underneath the main temple in Kyoto, and I'm not going to say that right, but I mean, I was like, that's the scaffolding that supports the whole building above it. And then these are the granaries, which are 800-year-old granaries, and the idea of repetition and stacking and simplicity was really appealing to me. And this is sort of the connection we ended up with for that building. It's just a big piece of steel that just basically is epoxied in on both sides, and then we have bearing screws that you see here on the detail on the left, and you can kind of see these holes in the middle. Those are drilled up to the height of that, so we can put a series of bearing screws that the metal plate then bears on, and then these ones here are for safety on the lamination, just to, you know, for 50 years from now, somehow something happens with the glue. But it was really exciting to see it. You can sort of see those are the pieces here. That's the only steel in this connection on this entire structure. Everything else is sort of stacking. So this is the 2 screws where they sort of stick the thing together, and then they graft the beams together. And this is just showing you that's it. Basically, that's all goes together, and then those things get stacked on top. So just the character of the space. You know, one of the things we really try to work on is like, and I think other presenters talked about is like the building systems are so important. So thinking about a way where with this double stack system we can put the mechanical up there, but you never really see it because it's all sort of hidden away, even though it is exposed. And then this is the backside of that building, sort of, and the facade is a different take. It's actually a silver and a dark, but with a very deep extrusion kind of. It's a little, there's some stripes in there, just a lot of them, and a little bit, related to what they do. The Oregon Conservation Center, oops, I'm not good at this, sorry. Let me go back. Okay. I have to point at this, yeah. It's the headquarters for the Nature Conservancy in Oregon. It was a really kind of exciting project for us because they have this not very nice existing building. And I remember when I talked to them, I said, oh yeah, we're located here. And it's like, really? Because I've literally driven by your office like 3,000 times and never noticed you were there. And Oregon Conservation, what's interesting about the Nature Conservancy, they're actually the largest holder of private conservation kind of organization in the world. They preserve millions of acres throughout the world, and they have large holdings. And they wanted a building that really expressed some of their values. So we said, well, we could we wanted to first sort of conserve the existing building and rework it, and then we wanted to add a pavilion that would allow them to have events to convene organizations that are related to conservation together. And so one of the things we wanted to do, this is the existing building, kind of get a sense of what we had. What we wanted to do was look at every material choice we were doing in the building and see if we could connect it, and even the design choices, connect it to their mission. And one of the things we did is we wanted to use FSC certified CLT and glue-lams, which is very relatively hard to do in the United States. I know that's pretty common in Europe, but it's not that easy here. We worked on the facade and sourcing juniper, which is a kind of a native tree to Oregon, but very invasive because of forest fire suppression. And we were looking at a way to use that on the facade, and then some of the ceiling material came out of a preserve that the Nature Conservancy was restoring. So we wanted those materials, even if you didn't know it, when you looked at it, that there was a story behind it, and that the material, that when you walk through the Nature Conservancy, you might have a sense of, hey, this material comes from this land, this is from our preserve, this is connected to our mission. And then the landscape would also have that same sort of expression. And we developed this convening space, which was just a kind of unusual space in that we had to match up with the existing grade of the existing building, but we also wanted to create a loftier space. So we came up with a system where there's a series of 7-ply CLT planks that basically hang low from the beam you see here, and then on top of that is a green roof. And then it pops up around the exterior of the building sort of to connect to the surrounding neighborhood. It's a very visible site within Portland. They have like 5,000 people drive by this site every morning or during one day. And one of the things that was great about when the building was done, this is some of the images of the offices. Somebody came into the building and said, oh, I'm so excited the Nature Conservancy is in Oregon. And they've been there for like 40 years. So this idea of architecture having the ability to create an identity for an organization was, I think, still really important, in addition to all these things that it can do in terms of your experience and in terms of impacting, our future, in terms of global warming and other things of that kind of importance. Just some images of the construction. I won't get into the sort of design of the veil, but it was really to think of the this sort of heavy or kind of CLT building, but then when you experience it from the outside, it seems like it's floating. And that was something we really, like, it's sort of inspired by these amazing oak trees, these oak trees that have these cantilevers where you're sort of afraid to be under the branch. And that was something that, we wanted, and this is one of my favorite images where you're sort of in this outdoor space, and that's the conference on your right, and you're looking at, the street context of Portland. And then this is a massive cantilever we have up top. And behind these beams, actually I go back, because I'm just gonna, we always want to try to do one little thing that's a little crazy, even if it's little. And this was that those columns, those mullions actually support the whole cantilever there. So all the mullions in that pavilion are structural. And we wanted to point load them, but the city wouldn't let us. But I'm kind of glad that they made us put the beam in, to be honest with you. So that's just the kind of character of the facade. We worked very closely with a fabricator, in outside of Bend, because people are like, you can't do this facade, and this was a really tight budget on this project. So it's one of those things that I think that I love in architecture is like I just love to connect with the fabricators and sort of interrogate them to find out how far you could push them. and we become friends in the process. I don't want to have them go out of business. I don't want to do any of that kind of stuff. But I think they get really excited about this. The pattern that we did here, where we flipped it and folded it, it's quite simple, but has a really kind of amazing quality. Sorry. Next project I'm going to talk about is called Red Fox Commons. I don't do the names of these projects, just so you know. But this was almost a kind of hybrid of what I would call old and new material, old and new sort of large timber material. It's 2 warehouses in Portland. I actually live right up on the hill there. And 60,000 square feet. These were built in the 1940s. Just to give you a little context, is what Portland kind of looked like at that time. I mean, pre this is in the turn of the century, sort of shacks on the hill. And then in 1905, we had the Pan-Pacific Lewis and Clark Centennial Exposition, and this is what happened. This was a lake at the bottom there, and then you can see Mount Hood in the distance. So this was a huge thing. They had, they were boosting Portland. 500,000 people came to Portland for this. And in the process of doing that, they built, this is sort of westward, the course of empire takes its way. That was the sort of, that was the world then. And then one of the buildings that we're so sad is gone is the Forestry Building that was built in 1905. And I wanted to show this because if you read the thing at the bottom there, it says, we talk about mass timber. That's just kind of, this is mass timber. That one log weighs 51,000 pounds, 6 feet in diameter. And unfortunately, this building burned to the ground in I think it was in the 70s, because they had a little electrical fire, and I think it burned for like 5 days. Something insane like that. But this building is right around the corner from where these warehouses are. And just some more like fun sort of things about wood in Oregon, 8 million feet of timber, Columbia River. This is how they used to like transport timber in the river, where you could just see those are all these huge trees that they would chain together into a boat shape and bring them down the river. So these are the 2 existing buildings. They were in sorry shape. They were just tin sheds, and they had this crazy number of mezzanines. This is a place they used to have raves, all kinds of things happening here, and this is sort of what the space felt like. This is after we cleared it out. You wanted to save all this stuff, but it was just literally a tin shed. But what was incredible to me is that they don't build these types of buildings anymore. This has a 100-foot span, 2 little columns on each side. And then the other building, and then they had filled it all in with all this junk. These 2 buildings were built originally separately, then they kind of slowly over the years put it together. They were built around 1945 during the war. They built hay balers here, so they helped win the war with hay balers. And this is the other structure. It was actually equally interesting, but it had a flat roof. So we figured out a way to like seismically retrofit these structures. But in the process of cleaning them out, we salvaged about 5,000, like a linear mile of 4x12 plus larger beams, and we stored them away. We're like, okay, we can do something with this. Pretty rough, you know. These were used for the floor, 4-inch thick wood used for the floor. And so we sort of said, okay, we could put those together and create a bridge to reconnect these buildings. So we classified all the wood, and then we came up with this system with our structural engineer, Eric McDonald, who's now at Holmes, was at KPFF at the time, to kind of screw laminate these beams together. So in the middle is a new piece, sort of smaller, and then on the outer side is all salvaged. And they put it together, you know, in the warehouse adjacent to it. It was like building this sort of like, you know, mass timber factory. And then we put it together this way. And it kind of looked like, when it was done, it kind of looked like a seafood restaurant. You know what I mean? And because I was like, God, maybe we shouldn't sandblast this. And then the superintendent's like, yeah, it kind of looks like a seafood restaurant. And I'm like, yeah, we're going to sandblast it. So you can kind of see on the right there, the sort of basic kind of way we sort of put these beams together. And they were really gnarly. These guys were like, you know, having to jack them into place to kind of get them straight. And then that's sort of the result of, you know, the space. And the way we kept this in the project was, it's also the handicap ramp that connects the two spaces, and we only needed one elevator. So that was sort of a way, there's no way they could take this out and do the building. But it was exciting. That bridge you saw there was just, you know, made in one piece and then just brought as a 60-foot bridge, you know, on a truck, and then rolled through one of the buildings and just hung in place. So this is the lower area. And it's great. I mean, some of the workers on that, they would call it the old growth atrium. I know that's probably not particularly PC, but it was kind of interesting to see their thoughts about it. You know, people that have had a connection to timber, you know, these folks, and just some images. They really wanted to use the you know, siding that aged, sort of the Corten, and I was really skeptical about it because I was worried that they wouldn't understand that it would be gray for a while and then it would do all these things that are kind of crazy. But it's really quite, you know, beautiful, and we worked really hard on the detailing of the metal facade to kind of keep it as clean as possible. I'm a big fan of, like, identify your rainwater leaders right away. Where are they going to be? How are they going to work? So because that's really, this whole facade's about rainwater leaders in a corner. And so we worked on that, and then we had this garden sort of connection, and you kind of see how it sits in the city. Some sort of views of how it. One of the things that's great about being in Portland is we do have these connections to the trades. You know, at least over the last 10 years, or actually 16 years, I've really developed pretty strong relationships with different metal fabrication firms, different wood firms. We kind of know each other, and it enables us to kind of, on a pretty tight budget, do some interesting work. So the view, the only thing we did to this building is we added that north-facing clerestory. So everything else, and we added a new mezzanine out of glue laminated timber, and then windows, you know. But it's sort of, in a way, it's like, what's old, what's new? That's okay. Doesn't have to be necessarily. Can be. I'm okay with a little bit of ambiguity. I'm going to end with some, because we have a couple other projects, but I thought it would be interesting to talk more about some of the stuff that we do sort of as research or for fun. I feel like, you know, I guess it's been 4 or 5 years ago, when we started to do Albany Yard. You know, like I said, D.R. Johnson at that time didn't even have a cutter, you know, to cut their CLT. But we really wanted to find a way to kind of get them into a building, get their material into a building. So we really designed that building around their capabilities so that they could be successful and we could be successful. And we sort of have a similar relationship now with the Frères. They're two brothers. They're sort of a timber family they've kind of really taken the leap, built a $28 million mass plywood plant. And so we've been working with them now for, don't know, it's been 2 years to sort of see how we could use their materials. So we did this pavilion as part of an exhibit for a really amazing architect named John Yon, who was not only an amazing architect in the 30s, but was also an incredible conservationist in Portland. And as part of that, he was the first architect, I think, in the world in the 1935 to use plywood in low-cost housing. So there's a lot of history in Portland because we're in Portland that people don't know about. And he knew Philip Johnson, the Museum of Modern Art, so we wanted to do something in the latest generation of plywood as part of an installation for his exhibit. So they had this, let's see if this video goes. This is Frere's, that's their log pile. They go through 5,000 a day. This is sort of how plywood is made. So these logs get soaked for 24 hours and then they unroll them. That's basically, the log being unrolled. If you've never been to a plywood plant, it's kind of, I'm not saying that you'll get that chance, but it's pretty amazing. So they have this whole veneer factory in place, and they were able to do these, at this time, this was a couple years ago, they were able to do these 4-foot by 16-foot panels on on their preliminary press, their test press. So all we did was cut 4 of the panels in half, and then we worked on sort of a homage to plywood, where the gaps between all these basically frames is like 1 1/8 inch, which is the classic structural plywood dimension. And then we sort of tested out the different cantilevers and installed this at the art museum. It was installed in 1 hour, which is good because the crane was really expensive. But that gives you kind of a sense of that. And it's still it's like, you have like favorite little projects. This is one of mine. So just some views. You can sort of see these are just full cantilevers. So kids would just walk around this thing. It was really great to kind of see people interacting with the material. And this isn't just the architectural version of structural plywood. This is like fully engineered. And this kind of odd connection you see here is based on the fact that it's a very long sort of angular fishhook connection that creates, they can do 12-inch thick by 10 feet by 50 feet panels. It's super amazing what they can build. So just some more images of that in their shop. And I'm going to end with, we said, okay, we've done this sort of square thing. Let's try out something a little crazier. So we've done a series of pavilions for Frere's at the Mass Timber Conference. You might have seen that we did this one last year, and we did another one the year before that I'm not going to show. But the program was always the same, was to kind of create a focal point in the conference so that people noticed who they were. and they needed a place to sit, and they needed a place to show their products. So in this one, we took the opposite kind of approach from the other pavilion, where it was sort of all about the kind of wide end of the panel. And we said, well, could we do something that's purely about sort of the end grain, like the cross grain of plywood? The expression of it is very much, and this is their plant. You can kind of see it here, and that's our sort of plywood iceberg that we developed with them. But we wanted also something that was, if you've been to the convention center, or many convention centers, the light is so harsh sometimes, it's terrible. We wanted also something that would protect people from that terrible light they usually have in convention centers, so you could go inside and have this different type of experience. So this is what we came up with, and it was pretty crazy, I have to say. We probably wouldn't do this again. I don't think Frere's would do it again. We didn't really know what we were getting into, because we were like, let's try to push their digital fabrication capabilities to kind of the limit. And so we came up with this design. These are all cut on their Weinman system, which is, I think, the largest, of its type in the United States. So this was sort of, it was built in 2 weeks. And we came up with this sort of idea of I was almost like, those great little dinosaurs that you got as a kid, that you put together, kind of crossed with the programmatic needs that they needed for their piece. And we wanted something that people would really draw people in and really sort of be connected to the materiality of these items. So I'm going to end up here, but this gives you some of the sense of the character of that space and the scale. We had to we assembled it and put it into the convention center in 3 different pieces. It's like 25,000 pounds. It was, it was a little intense. But you can see the quality of the machining that they have it's pretty unbelievable. I mean, that we were able to get this just straight out of their machine with a little bit of finishing. And that's it. Thank you very much.
Thank you, Thomas. I think it's important that you've outlined, as others have, the range of maybe the conventional, even trabeated structures moving to the crazy, intense, and more flexible structures. We move forward to our next presentation, Jeremy Smith. Jeremy Smith is the design director at Irving Smith Architects in New Zealand, where he's led a range of ISA's design innovations and continues to demonstrate an ongoing commitment to innovative, sustainable, and research-based design with a particular focus on timber, backed up by national and international awards and publication recognition, ongoing research and teaching. Irving Smith's work has been internationally recognized, including the World Villa of the Year at the 2017 World Architecture Festival in Berlin, and otherwise being given high commendations at the World Architecture Festival in Singapore 2015, as well as Amsterdam this year in 2019. Jeremy Smith.
Now, I woke up this morning in the very south of India. So I'm going to stand down here in case I fall off. I was in India judging the Indian National Architecture Awards. And some quite interesting things happening. The best work was amazing, but the people in the mines were extraordinary. And what they were talking about, some incredible Indian scholars, was that India is progressing so quickly that they need to do reflection, just what we're doing here. And a fantastic educator and architect called MacKeith who, you know him, Peter? He was amazing. But he said, we need to stop doing this. More of this. Stop boundaries. Make collective. Stop being the master. I've lost the in my pocket. Stop being the master. Be the healer. And it's a nice kind of way of thinking about timber. Okay, so I was here in February talking about some research and some broader work, and I'm going to start with the same poll, the same question. Who's been to New Zealand? Hey, there we go. Right? And was it a long way away? Yeah, because the first thing to know about New Zealand is that it's a long way away. So in February, when I went to look for a map to start this talk, we weren't even on it. If Australia's down under, we are way down under. It doesn't matter where you're coming from, we're the last stop on the subway. There's no roads coming to New Zealand. If it's coming on a boat, it's coming on a boat. New Zealand was the last inhabitable landmass to be inhabited. We are Moana. The Polynesian people arrived 800 years ago. Colonization, a little over 150 years ago. And so when New Zealand was getting going in colonization, New York looked like that. But the colonists, when they arrived, said they could hear New Zealand before they could see it. And so the second thing to know about New Zealand is that it's a country of trees. We separated from Gondwana land before the mammals evolved. We have no mammals. We have one, actually, a bat that must have blown in from Australia, and it's now flightless. So we were the home to the moa, the biggest bird ever. Home to pukai, the biggest hunting bird ever. But both these birds are extinct because from almost the near total forest cover that greeted the first inhabitants, less than a quarter remains. And our landscape has been changed with unparalleled speed. So it's been changed from forest to pasture, leading to this colonial boast. What in Europe took 20 centuries and in North America 4 has been accomplished in New Zealand in a single century. Woohoo! I did that in India and they all clapped. I was going, no! That's not good. So our architecture has developed in wood. We don't have any steel and we have limited concrete. If it's coming on a boat, it's coming on a boat. And now the way we build won't look unfamiliar to you, but it's not unlike the first Maori houses and the early colonial buildings. Our subdivisions were built out of native timber, and they're now built out of plantation radiata. Because what happened in New Zealand is that where the farmlands failed, where they were too far away, they were too steep, the bush either regenerated or they planted pine trees. Now my thesis was looking at the regenerating bush and looking for ways of New Zealand to be part of conservation and build in regenerative forests. And it said, if the nature looks better from inside the Farnsworth house than outside, it relies on controlling the landscape. If you don't, and a forest grows, then your buildings fit to the landscape can't be as good before and after. So modernism asks you to repeatedly finish the landscape so you don't have to change your building. It asks you to use a lawnmower. So it was a great analogy for New Zealand, and the thesis looked at how New Zealand could iteratively change its buildings rather than repeatedly finish the landscape. But the pine forests are massively important as well, because if we didn't have them, we would have a whole lot less native forest. And if you look at New Zealand, and it really is that green, and you take away the grass, you're left with indigenous forest, which is the dark green, and you're left with the plantation forest, which is the light green. And the two buildings I'm going to show you, no surprise, are centered where the plantation forests are, but also the industry. Now, what is surprising is that we haven't built public buildings in timber. Yet, we live on both sides of a plate boundary that grows the same speed your fingernails grow. And so they had grand plans in Europe for New Zealand. And the heavyweight construction wasn't easy to hold on to. It wasn't any easier in Napier in 1931, and it wasn't any easier in Christchurch in 2011. So if you're a practice like ours that likes solving problems, trying to help New Zealand, this is a good one. How can we use timber in bigger buildings? The third thing to know about New Zealand is there's not many of us. Again, we're not even on the map. I'm not making this up. This is just what happened. We're not there. But Sydney, you know where Sydney is over there? We're smaller than Sydney. So put on one light bulb over there. Now, if you're small, there's not many of you. You don't have much factory. And one big job can just stop everything. And really in New Zealand, it's not much different than it was in colonial times. If it's coming on a boat, it's coming on a boat. You have to work with what's there. So we can't innovate from outside the industry. We have to innovate from inside the industry. We have to use what's in New Zealand, what we have. Now, this is just to make you come, because timber buildings or houses are in very beautiful places in New Zealand. There's a lot of coast. But I'm just going to quickly spend a few minutes just showing you buildings that aren't timber. Because we think about timber buildings just like we do every other building. We're a long way away, we've got no steel, limited concrete. You have to think about where your materials are coming from in New Zealand and how you're going to make them. But first I'm going to just quickly show you what we're doing at the University of Auckland. So we run a course called Changes, so it's got a good theme song. No, I used to stutter that, but now I can say it, right? But what it does is it asks students to prepare a strategy for change and then to test it, with each week accounting for 10 years. And more, what's really interesting is the students are doing this in timber, because timber gives you the ability to change your buildings. And so it's been interesting over 3 years, we haven't actually led it and said, you must do it in timber, but it's growing as an interest, I think. And if you look at the two cities over 2 different years, it just shows that cities change a little bit through landscape urbanism, plants, seats. They change massively through buildings. Someone builds big next year, you have to change. So there's an opportunity, we think, here. So I'm just going to show a few projects so you can see how we think. And you have to understand what you're doing in New Zealand in order to be able to solve the problem, or to ask the question. So to build in a forest, you have to understand how the forest feels. When the forest gets hit by a cyclone, you've got to work out how the building needs to be refinished, and then do it in a way that the building suits its new clearing, but in time can iteratively change to a forest. If you're doing a concrete building in New Zealand, New Zealand's small. These are small towns. To do this building, the whole concrete yard gets turned upside down. They've got to pour each panel twice. You've got to say please. We make it easy by making them all rectangles. So the house is a barcode. If you're doing a building in metal in New Zealand, we make everything the same. It's coming on a boat. If you're doing a house in a really isolated location, we'll often make the walls out of the roofing. It's really hard to send things back. And so you have to get in and understand the question. New Zealand's most contaminated site that they remediated, and you put a spade in more than 30 centimetres, and you need people in gear. Once you understand what they've done, you can invite in the services engineers to put in a waste system in your site and then build caps on top of their pipes that the community can build on. You've got to find a way in New Zealand. One of New Zealand's most protected buildings. You just understand that it's got to become this just through seismic anxiety. Just worrying about earthquakes went from that to that. So in fixing it up, we'll never do another bauble. Well, I hope not. Very hard. But you have to understand how you can fix something and improve it with what you've got. So that was in 1895, the incredible timber ceiling. So just as the last of this little series, in turning an abandoned big box retail into a library in a part of New Zealand which has an oral rather than a written history, a Maori population, you've got to understand that you've got to get people into the building. So you gently put people on the building, then they might go inside. Now, none of this is about money. None of these jobs are expensive. It's purely about thinking. We can't afford German display cases. We make ours out of showers. Everyone has a shower. Every town in New Zealand. To make the screen, this is a fishing town. This is off a fishing boat. It's a floor on a fishing boat. So there's no point waiting for something to come on a boat. You might as well use a boat that's already there. We talked to these guys. So when the New Zealand government, this is the job that it's Thomas, isn't it? Yeah, we went talking about. And do you sleep? You've got a lot of work. This is the one you were talking about. So when the New Zealand government said, we're going to run a national timber design competition for New Zealand's landmark timber structural building to promote timber in larger buildings, we gave them an answer that was achievable. This is LVL, laminated veneer lumber, one factory in New Zealand doing it, just started. It gives you bigger spans. We'd been playing with it. We knew how to remove the glue and to finish it. We knew how to accept knots. started with a table, which we put into a house, which we used the LVL as a structure. Everybody else in the competition went for massively complicated moment-resisting frames with bells and whistles everywhere. We just looked for a post-beam junction that would give us a commercial span that was achievable in a provincial town in New Zealand, and where all the timber could be grown, milled, and erected within 80 kilometres. But we won it because we handed in a 1/3 scale model that looked so easy and so understandable, it looked like we'd blown it up on a photocopier. And it can just have 3 bolts, because this is just doing gravity. We said to the engineer, we just have to make this so simple that it's not going to be able to be done. How can we put all the earthquake loads into a few key places in the building, and all the engineers can just concentrate there? And this is what you were talking about, Thomas. So we did these post-tensioned rocking timber shear walls. Hadn't been tested, so we tested them. This is without the pivots, I noticed the other day. Yeah. But the building itself is an art school. So it has kind of a big shed of wet areas, a 3-story vertical atrium, a services wing, and a studio space opening south, that's the away from the sun, southern hemisphere. So we just gave it a very, very simple post-beam structure, 9 metre span and 6.6 bay, I think, and 4 pairs of rocking shear walls. So that all the complexity was just in 4 places. Here they are, 4 metres wide, 13 metres high, I think. And all they are is a shoe at the bottom, some McElroy bars that run from the top to the bottom, which you crank up, and a pivot, 2 pivots. They're made out of 63mm, which is the I don't know how much the inches, the standard billet thickness, and 3 layers, and the middle one's just removed. And in the middle, we put a fuse. So in an earthquake, they rock, the fuse can be replaced. It yields. So the idea is that the building can be reoccupied. There might be some linings need to be replaced, but the building can be reoccupied the next day. So here we are, we're on site, and we're instantly pleased we've done an incredibly easily post-beam detail. We kind of came up with a way of flange hanging the floor system, so it's effectively like double T's. And then at about this point, we had started to have architect friends ringing me up saying, "What is it? Don't get it wet." Do we all have that problem? But it's soon clad. And all our timber is inside in our buildings. We don't put any of the structural timber outside. I'm sure someone else has said this already. But when you walk in a forest, you don't see timber, you see bark. Someone said that? I don't know where it came from. Probably someone here. I've ripped it off someone. So the world's first post-tension multi-story timber structural building is in fact a big house. Made legible to teach the New Zealand construction industry, but it's also a community art school. Now, we'd just finished and they had an engineering conference in the building from all over the world. And they said to us, "What kind of tools did you use?" And we said, "A really big hammer, a really big chisel, and a skill saw on a jig." And when we needed to, not that I did, when they needed to drill the pivot, they turned them over with forklifts. And the guy selling the German tools was pretty upset. But then he went to the building and he was happy. He could see the timber before he went inside. And we're showing to the community how the building's made, but also how the art school works. So everything is legible. There's these incredibly simple post-beam details. And we have a code running through the building. So if it's structural, it's clear. If it's non-structural, it's white or it's bleached. So from gallery spaces to teaching spaces and studio spaces. So there's the fuse down the end. And we have a very simple kind of white lowered ceiling, which just means all the exposed surfaces, we just go that way. When you get to that white thing, you can do whatever you want, but when you come out again, go that way, no bends, because you can't penetrate the timber. So everyone got really excited. We'd changed the landscape. And there was government reports on its carbon positive footprint, PhDs studying the moving bits and pieces. But it was all a bit quick, because the Christchurch earthquake came. And who do you think rebuilds a city after? This is New Zealand's second biggest city. So it's only 250,000 people, but it's flattened. Who do you think rebuilds it? It's not architects, it's insurance brokers. They're rebuilding the city. They're rebuilding it in steel and concrete. So the government kind of worked this out. You know, it's like that TED talk, you know, that the bravest person isn't the first person to get up to dance, it's the second who starts the crowd. It's exactly what happened. So the government, we got involved in doing a kind of a report on what was the cost difference to try and work out between steel, concrete and timber. They were all about the same. Timber should have been the cheapest because it's not coming on a boat. But it was new, so it wasn't. We had a site to do the first building, but when they planned Christchurch, it was in a park. And they replanned it. So no job, no site, no job. So we just kept on going. And then what's really interesting is that you can see in the next couple of buildings when a new machine turned up on a boat. Makes a little difference. But you can see more. We've actually innovated by removing the innovation. So we did a little small office building. It's got concrete perimeter walls for fire rating and a gravity structure. Again, everything's legible. It's got a really simple corbel to hang a pre-made concrete floor beam onto it. The next building, a CRC cutter's turned up. This is the New Zealand equivalent of Walmart. It's very small. There you go, you can see it. We can now cut the beams. This is the cheapest way of doing a floor in New Zealand. It's a pre-stressed concrete floor. But what's more interesting is that this is a 2-story building. We started doing fuses with nail plates. So when the New Zealand Timber Research Institute ran a competition for a 2-story high innovative science hub, we gave them an answer like another table that we just made for the office. And we said to them, at 2 stories high, you don't need all that stuff. It's not the right answer for the industry. Everyone else gave them versions of our NMIT building, the previous one, or, again, really, really complicated post-beam junctions. We stripped away the elements and put them into shear columns, and then used nail plates you could buy from the local hardware shop, just like you would on any timber building on poles between the bearer and the pile. It's just a bigger building. It can grow. And we could build, so we said, the first bit in 30 days. And we won. That was great. But we'd innovated our way out of a job. They didn't want to build it. It wasn't innovative enough. But they then said to us, come, this is where all the timber testing in New Zealand happens, all the scientists. Come and do the hub building, the entry to our campus. And use more timber, please. Didn't have enough. And I said to them, you've got it all wrong. we shouldn't be grading our timber buildings by how much timber we use. We should be grading it by how little we use. Sustainability isn't more. Sustainable is less. So we went looking for how we're going to use less timber in this building. The first iron bridge, Andrew, you'll know where this is, I can't. It's coal something, yeah? Yeah. It's made like a timber bridge. They hadn't worked out yet what iron was going to be able to do. So why do our timber buildings look like steel and concrete buildings? So if you think about the load transfer that happens in this building, it runs along, comes to the column, does a massive big 90-degree turn. If you think about a tree, the strength of the tree follows the grain. So we gave them a 3-story high timber diagrid, where the strength in the building follows the grain in the timber. And we remove all the concrete. So the concrete's 40% of the weight of the building. So you have here, I was laughing at them last time, you have these water towers sitting up high, like a golf tee with a golf ball on top. Disaster in an earthquake. So we make it all timber. And in the middle, again, we put a fuse. So after an earthquake, we can replace it. And this could be a taller building. And the building itself sort of nestles into the campus, and it's a 3-sided, there's an atrium there, and 3-sided building. And on the bottom, it's got a cafe and kind of display and come inside stuff. And as you go up, it has the scientists working at their desks, which, they've gone from little cubicles to an open plan area. They weren't very happy, but that's not our call. And then on the bottom, there's a double skin for environmental. And then we glaze the building in a whole lot of fritted glass so that the campus can say to the community, come, walk inside our forest. But we're not finished. We haven't at this point solved the problem, which is these things. The steel junction. So there's lots of steel in timber buildings. And the problem is, it's really hard to fire rate. I don't know if you've been talking about that. The timber goes against the steel, or the steel goes into the timber, and you can't, the intumescent coating doesn't work. All this stuff. So our timber building, whereas previously we'd thought about it as sticks with a jointer, we're now thinking of it as prefabricated diamonds and triangles. And there's a revision from that one. We did this during the working drawings. Like, we had quite a lot of speed on, and that's what we gave them, that one. And then during the working drawings, we changed to this one. And the building's the same, but if you look at the node, it's different. And what it is, it's LVL, so laminated veneer lumber, but effectively we've made glulam at the junction. I'm going to put the mic down. It's just that. It's like cabinet work. It's got some really clever engineering in it, but it's quite understandable. And so we attack it in the corners. And this is New Zealand, so there's two factories that could do this. There's two. One in the North Island, one in the South Island. So we turn the whole lot into 6 bits. If we had 126, they're not making it. But each one of these bits, it'll take the whole factory, and it'll just be this bit they make. So there's our client testing it. That was quite interesting. Hope it works. So that was after the test, so it did work when they tried to pull it apart. And here's the first one being made. And we're inside the industry. These guys have made something similar before. This is just bigger. But what's remarkable is that the size, this is quite a distorted photo, the size has changed. So usually the timber's the same size as steel or concrete. So my maths isn't going to be good enough after being in India for this. But just the NMIT was roughly 500 millimeters square. These are 300 millimeters by 100 millimeters. So what's that? That's 12 by 2. 4. Right, there you go. 12 by 4. So they're less than 25% the size. Here we are on site. So they come individually and they stack in a line. And in the corners, we have half ones. That gives us the tolerance. And at the junction, you can see how small they are. That's where the fuse goes. So, looks like a bit of a forest of trees. And just for a bit of scale, you can sort of see how big it is here. So this is the bottom 2 floors. So you can see now they've put the beam that runs in along the back, and they're dropping in a CLT floor, and there's the CLT lift. So then, while I was in India, this turned up. This was maybe just before I went to India. When did I send it to you, Peter? Just before? So you can see what's coming. And so now we're inside, and you can start to get a feel of the sense of space. So this is looking towards, this is the atrium in here. It's kind of a horseshoe shape around it. So you can see there's a really simple corbel on our die-grid, where you just widen it to support the beam. It's just what you were saying, Thomas. Just trying to make it things as simple as we can. There's those nodes with the finger jointing. And you can see how small the timber is. And they work exactly the same on the outside of the building. So there's a glazed curtain wall system that goes around it, which just spaces off the beam with a clearance gap. And you get a sense of the transparency through the building. And then these are the new bits turning up. This must be while I was in India. The new bits turning up to go on top. Looks like they've been dropped off by a boat, but they actually came from just up the road. We might have. They actually have got a picture somewhere of the next floor on. Anyway, it's not there. Left it in India, but the next ones are now on, so it looks even better. So there's 3 things you need to know about New Zealand. We're a long way away. We like trees. And there's not many of us. So we're innovating from inside out. But now there's a 4th. And the 4th thing is, we're making things smaller. 4 things. So we've changed the way that we're thinking about how we're making our timber buildings. And if we go right back to the analogy at the start, that the Farnsworth House, the great steel building, if you start to think that we can't control the landscape as we thought we could, well, if Mies had built his building out of timber, presumably he could, out of all the amazing timbers we've got now and the technology, then his building must be in a better place to be adapted and to be changed. So by making things smaller, it has to help that, besides the sustainability of using these. So, as we we're quite excited by this building. And we're innovating from inside the industry out. And it's coming to you on a boat. Thank you.
Thank you, Jeremy. I'd like to ask for an additional round of applause because Jeremy literally arrived from India, having sprinted through O'Hare Airport to get his flight to XNA. So thanks, Jeremy, for that extra effort. I want to suggest a 5-minute break only, as we've scheduled, so that we can begin to condense our schedule slightly. At the end of the day, we'll return with a sort of final crescendo with Kelly Harrison and Erin Dorf. 5 minutes, please. And we move from the antipodes, in a way, I won't even say back to the center, because each of us has our own centers. But we're going to move from one exotic location to another exotic location as I introduce Kelly Harrison. I contacted Kelly in part on the recommendation of Andrew Waugh, and I did not get an immediate response, which worried me. But then when I did get a response, I understood why, because Kelly was in one of the few places in the United States, apparently, where there was no wireless signal, or at least temporarily no wireless signal, because no wireless tower had yet been set up at Burning Man. And this is what Kelly was working on there at Burning Man, and she apologized for having to, or not responding, because she was in a remote location preparing for a music festival. And I thought, are you with Burning Man? And she said, confirm that. So she can say a few words about the Burning Man project as a bit of a immediate exclamation point leading into her presentation. But Kelly has over 13 years experience as a structural engineer, and since joining Haney Tillett Steel, or is it Haney Tillett Structural HTS Structural Engineers, has worked on schemes across all sectors and at all scales. Her experience ranges from small-scale, exceptionally detailed private houses to large-scale commercial developments in the heart of London. In 2015, Kelly completed a new walkway within the Science Museum London, which was opened by the Queen and won a structural award in 2016. Kelly's a passionate advocate of sustainable construction, and following a project which extended an existing RC frame with a new lightweight cross-laminated timber roof, has proposed similar constructions to many clients. And there's, again, an enormous number of projects that she's worked on in this regard. She's worked on several educational projects and has recently completed an extension to Grade 2 listed buildings at Charterhouse, Surrey, to provide a new chemistry block in exposed CLT. Kelly runs a research group in collaboration with London City University into engineered timber innovations, as well as a timber focus group for timber enthusiasts inside the firm. She sits on the advisory committee for the UK's Timber Research and Development Association, as well as an editorial board for the New Steel Construction magazine, to be ecumenical, and the British Constructional Steel Association's monthly publication. Please join me in welcoming, not straight from Burning Man, but certainly from Burning Man, Kelly Harrison.
Good afternoon. Are we on? Yep. Good afternoon, everybody. Yeah, sorry, we've got a couple of slides here just to show a bit about what I was doing at Burning Man, but it wasn't part of my original talk, so apologies if I mumble my way through it a little bit. Yeah, we got together a group of people. I worked with an architect on some crazy staircases made out of plywood a couple of years ago, and he wanted to do this at Burning Man, and we, as a company, just like doing unusual pavilions and structures of all sorts of shapes and sizes. So we agreed to do a pro bono project, looked into it. Everything was cut from a standard sheet of birch ply in Reno in a factory on the CNC machine. These kind of dinosaur-shaped ribs, we called them, were created from 3 sheets of 3/4-inch ply, glued and screwed together. They were all grooved out on the CNC machine as well, and holes put in. All the joists were notched in, so there were notches in each of these ribs, which were also chamfered because the joists all came in different angles, which you might see from the next slide. Oh, is this working? Sorry, not quite working. There we go. This is just sort of the next stage on. Another bay had gone up here, but yeah, the joists all go in at different angles. Some of them are step joists, which are crazy zigzag ones. Some of them are straight with holes through. And it created an undulating landscape in the end, which was to provide an amphitheatre type space. This was pretty remote at Burning Man. It took us about 40 minutes to cycle from our camp to the site. So it's right on the edge on what they call the fence. So it actually ended up being the sort of sunrise spot for everybody. If you go there at 7 a.m., 7 a.m., it was where everybody was, which was not how it was intended originally, but a really nice outcome from it. That's a sunrise shot. So it wasn't quite orientated for that. But it ended up being good. There's also a cool little balcony that you could crawl through and sit in a little nook in the back. Anyway, I think this is probably could be discussed at length in another presentation, but I'll move on to what I was actually going to talk about today now. Oh, a night shop as well. Forgot to send this one. Everyone's bikes. Okay, so what I wanted to talk about today was, when Peter got in touch with me about this, he asked for detail. And so I've included detail, and apologies if it's too much. But, what I'm going to talk about are 2 glulam-framed office buildings I've worked on over the last sort of 6 years. And, well, the first one being actually made of 3 phases. This is actually neither of those. This is a spa building we did for the Dorchester 10 years ago now, and this building's been open for 10 years, and it's really our first engineered timber building. It's a transfer structure over a swimming pool, which supports the columns on a radial grid over, and that transfer structure was one of the first sort of cassette stress skin LVL constructions. Zublin, who Tanya was talking about earlier, with the suppliers and installers for that. Which was really, that project was the catalyst for my director. So we are Untitled Steel. Steel is a person, we're not fabricators, which most of the UK think we are, which is why actually I'm on the New Steel Construction magazine board. But anyway, Andy Hayne, Mark Tillett and Tom Steele, and I worked with Andy Hayne, and this was his sort of baby project. He loves it, and it really took him off on a journey in timber, and having been at Hayne, a little bit about HCS there, and the directors now in or the management team. I started there 11 years ago now. It's only 12 years old, and I started a very young engineer, and we were only 11 people then, and we've grown to about 105 now. And that we have these are our approach notes that go in the slides. To be honest with you, they're written by marketing people. As someone who's actually worked there for 11 years, what our approach and what I love about working there is the attention to detail. We love working on architectural projects. I did architectural engineering as a degree, and it's all about the detail. Exposed structure is what we love and what we thrive off. But also, we say here research-based intelligence, which is true. We research our sites to the tiniest detail. We know we work predominantly in London. We know all the boroughs. We know all the archives. And in London, there's a lot of existing buildings. It's so dense. We became experts in using those existing buildings to the maximum, extending them, transforming them, and getting maximum potential out of them. And because of the architectural detail that we enjoyed, we did a lot of exposed timber structures in our infancy, mainly new builds, such as the spa. We did also several nursery schools, private houses, which this is one. But actually we started thinking, well, why can't we love using this material? Why can't it be used on a much bigger scale in the city centre of London, extending existing buildings, adding the least weight possible to those existing buildings, but also creating beautiful office spaces that are marketable, people want to work in. And so we started off on that track. So that's just a few practice by numbers. Another part of what we do is really, we talked about earlier, collaboration and sharing knowledge. We share knowledge weekly with the firm. Every Tuesday and every Friday we have lunch together. We have a nice chef that comes in, Mel. She cooks great, now vegan food, which a lot of people are not happy about. So I think we're going vegetarian from next week. But yeah, so we have lunch with each other twice a week to discuss projects, and to discuss on Fridays in particular. Each team gets up and presents problems and successes. And so today, to be honest with you, I've used this forum as a bit of a therapy session to get my problems and successes out there, and probably more problems than successes. This is just me, that's my team, in one of the buildings I'm going to talk about in a moment. We're all very happy because it's timber and it's nice to be in. Andrew talked earlier about the architects declare. About a week later, engineers declared. So we're very much part of that movement. We're looking in all our designs to be as efficient as possible. I mean, there was an awful stat that came out. I was at the Institute of Structural Engineers talking at a conference, a debate about this a couple of weeks ago. Engineers typically design buildings at only about 50% capacity. And that capacity is also based on loads, which are way more than we actually see ever. And so there's a whole discussion about that going on in our industry in London right now. We aim to design everything at, at least 95%. But then also we need to look at those loads. I mean, we design offices for, like Andrew was saying earlier, we don't have all the paper that they were meant to, that's written in the code that they were meant to have in them. And I think it was proved by Arup recently that you can't physically fit enough people in the amount of floor space that you have to design. And then we add another factor of 1.5 on top of that as well. And then we've got material factors, and then we only design at about 80%. So it's just crazy, and we don't need to be using that much material. So I'm not going to talk much about sustainability and climate change today, because everyone else has done that much more eloquently than I have. But my passion for this stems from that, and I've been promoting timber extensions and timber timber material to my clients for the last few years because of that. And I just want to share with you some of the lessons I've learned in doing that, because as we've heard from other speakers today, you can't just design it like a steel or concrete building, but we did. So I'll tell you how we got over those issues. So these are the two projects, Republic and Old Gramophone Works. I'm speaking to a Canadian developer a couple of weeks ago, and I gave a presentation. He said, "Your slides were great. It was lovely to hear about your projects, but all I really care about is how many square feet." So I'm going to tell you how many square feet, because I don't work in this all the time. I've got to read it. Republic is an existing sort of master plan of buildings. They were built in the 90s by Mark MacDonald. And there's 600,000 square feet of existing building. We increased that to 650,000 square feet, of which 35,000 square feet were glulam and CLT construction. Or Gramophone Works, this is a new, we have an existing building there as well. You can't quite see it in that CGI, but I'll go into that in a moment. This will be 92,000 square foot of office building, of which 66,000 square foot will be glulam and CLT. So Republic is complete now. The third and final phase got PC, I think, 2 weeks ago. And our Gramophone Works is currently on site. The timber arrives, it's meant to be November, but I think it might be December now, existing building problems. In case no one knows where London is, this is where it is, just in case. So Republic's in Tower Hamlets. Tower Hamlets is east of London. It's not far from Canary Wharf, which is our financial district. And you can see the buildings here. Now, this is the whole master plan of the development. Our 3 phases consist of this building, and the public realm between the two. These buildings were designed originally to be trading floors. They've got huge amounts of capacity in them. As existing, they were empty trading floors for people from Canary Wharf in a terrorist attack to move into without stopping trading. Well, for the 20 minutes it takes them to get there on the DLR, maybe. And that's what the building's being used for. It was empty and full of capacity. And so the development managers we were working for, who were funded by a pension fund, really wanted to renovate this area. It's a horrible part of London, to be perfectly honest. This is a massive road which leads down to what's called the Blackwall Tunnel, which is just one of the only tunnels that goes under the Thames, and so it's just chocker with traffic all points. And they really wanted to just make this a nice part of London. And so it's actually easily accessed from the DLR, which is the Docklands Light Railway here. And you just walk over this bridge and you're straight in this like lovely little oasis, which we've created now, which wasn't originally. So I didn't think that the screens would be this big, so apologies for the resolution. So we've got the import building in pink up there, that was phase 1. Phase 2 was the public realm, and the export building, which is just finished, is the purple one at the bottom. The import and export building were pretty much carbon copies of each other, 10-storey RC frames. So the import building we did first, and we probably started that project about 7 years ago now. We weren't, at the time, totally au fait with using glulam and CLT. And so the client wanted to make a big impression. They had a big sustainability drive. The architects wanted to create something dramatic. They had this huge atrium in the original building that just didn't need to be there. You still got a really big atrium if you infill these bits, which we proposed to do. And you know, it was a bit of a light touch, but we were convinced to do it. And they extended the building out the side in a metal deck and steel frame, because that's what we did back then. And so these are some shots of the timber going in the atrium. Connecting into existing concrete was fun. Getting it into a small site was fun. I've got a few more slides on that later where I'll talk a bit more about it. But there's a couple of finished shots over there. And it created a really dramatic space. And this building is super, super interesting to go in now. They've got gyms, they've got co-working. It's just really activated and a lot different to how it was before. It won a few awards at the time and got everyone a bit excited about refurbishments with timber in London. And so on the export building, which was phase 3, we learned a few lessons from what we did on the first one. We realised it was massive over-design to put all those columns in. So everything, the CLT just simply cantilevers over some beams which are fixed to the concrete columns now. But also everybody loved working with the timber so much that we wanted to do the extension out the side in glulam and CLT, which proved to be a bit of a journey, because we wanted to do it, the client wanted to do it, the architect wanted to do it. The main contractor wasn't so keen, as they often are. They went out as a value engineering exercise and found out that they were going to save a whole heap of money by doing it in steel metal deck. So we challenged that. Andy Hayne and I, we'd been going to quite a few timber conferences by now. We've made a few connections, and we got a few quotes for ourselves for this project that the suppliers agreed to stick to. And one of those quotes beat the cost plan with the steel and metal deck. On top of that, we could prove, because we knew the developer wanted to add more stories in future, which we're now in planning for, we could add another 3 on top in glulam and CLT, whereas we can only add 2 on top in steel and metal deck. And that really sold it for the developer. He was like, right, this is definitely what we're doing, and we'll nominate the timber guys. So luckily we got that through, and the project went ahead. So yeah, there's also an extension and there was an external walkway along here before. So this is actually more, which was an undercroft in the building, came back to this bay. So this extension down the side, although it seems like a small slither, was actually 100 meters, was that 330 feet long, and a couple of 2.5, 3 meters wide. It was actually a significant project in itself. Just a few nice shots of everything going in. obviously all the off-site stuff, we had to do a lot of survey work of the existing concrete. We had to design our connections to allow for clashes with reinforcement. We learned a lot of lessons in there. This is some finished shots now. Unfortunately, I've not had a professional photographer around there yet, so this is just me with the SLR, getting a bit excitable. You can see there's a few things that we probably do differently, and this is you know, this frame out here is very steel frame, and maybe that wasn't the best way to do it. We've got all the services underneath. There's not a lot of head height under some of those services, and it's been a bit of a complicated thing to coordinate. But I'll talk about that a bit more in a moment. The public realm in the middle of the two was a canal or a waterway, I think. But it was a bit dreary and horrible. So the architects, sorry, I've not mentioned, the architects of Studio Richard Howell Evans, they're quite a small firm based in London, but they do some really exciting stuff. And yes, they proposed to completely reconfigure the public realm, and they've created these lovely pavilions. We infilled part of the canal to create waterways and found new routes through for the water. We created a very biodiverse environment. And here's some of the pavilions going in. So the pavilions are CLT, sat up on massive stainless steel brackets off water-resisting concrete. And they were also then clad in a koya, which is treated wood. Now, how do I pronounce it? I've been trying to remember. Acetization, I think. Yeah, so it basically, it's guaranteed for 50 years and will not rot, apparently. So that's quite exciting. And a couple more finished shots there of that. Second project I'm going to tell you about the lessons on is Old Gramophone Works. So Old Gramophone Works was originally, surprisingly, an old gramophone factory. And then it was a recording studio. Apparently there's been some famous people in there. It's in quite a famous part of town. I can't name them right now. But it was this sort of crazy structure with these massive columns. And they stuck out a little bit from the roof. And so then we found drawings of the original building where you can see in the distance there, this is one of the original towers on the side. It was designed for another 2 floors on top, which were never built. So we managed to add another 4 on top in glulam and CLT. And that all sits on the existing column bases, which are at basement level. They're massive, big trapezoidal bases, which just sit straight on gravels, and it's right next to the canal, so they're water-bearing gravels as well. We've done a lot of detailed groundwork analysis with geotechnical engineers to make sure the settlement's okay, which it appears to be quite easily. So this one's on the other side of London, West London. Like I said, it's next to the canal. And it's in the Royal Borough of Kensington and Chelsea. So there's a few CGIs of what it's going to look like, hopefully. We originally had a concrete core, you can see here, but it changed halfway through the project. So now we have a concrete stroke CLT core, which I'll talk about a bit more in a moment. So yeah, I'll talk now about the lessons learned and give you a bit of a, well, I'll take you through my last few years of my pain. So acoustics, we started off on the import building and we had these details here. We have 5 millimeters of a polyurethane sheet. We then have 100 millimeters of a polystyrene insulation. And on top of that, we have a wood fiber and chipboard, another layer of about 38 millimeters, I think. And then we have a raised floor on top. That's what the acoustic consultant thought we needed, because they had no data for CLT. That was about 7 years ago now. When we got to the export building, they were like, okay, we don't need this 100 mil of insulation. That added sort of the same weight again as the CLT onto the structural calculation, onto the loads. which we felt was going to be a killer for CLT. We can't do this every time. And so, yeah, next one along, they had a bit more experience. They'd done some testing. They got rid of the insulation, but we still had the 5mm layer and the 38mm layer on top. We then worked with them on old Gramophone Works, and these are the details that we have for old Gramophone Works. A lot of these are not always for because of acoustics. Sometimes we just needed a different finish. You know, these ones are 50 dB. This one's 53 dB with a lightweight screed on top, and there's one down here with some cement board which gets the 60 that we needed over the cafe. But here we still have a 6mm, we have a recycled rubber. On top of that we got the chipboard and wood fibre build up again, and then between the services they've said 60% of the floor needs to be covered with some wool insulation to get to our 50 dBs, which I'm trying to challenge at the moment. And so I think Andrew will recognise this detail because it was sent to me the other week, because we've been trying to organise some testing. And this is one of Andrew's details, where you just have the CLT and a raised floor between two offices, which works pretty well. And so we've got all these build-ups because the manufacturers of the acoustic separation give us the dB ratings, or give the acoustics and consultants the dB ratings. None of them want to test this because it doesn't have any of their products in it. So we've got some acoustic consultants to go down. We were hoping that we were going to go down on Wednesday, and I could have told you the results today, but unfortunately we couldn't arrange it in time. But we're going to test this in the next couple of weeks, and hopefully we'll get some good results, so we can roll that out on projects going forward. Fire, the hot topic, yeah. First of all, we learn on the export building. Just actually going back a step, as engineers, Tanya touched on this earlier, we started off in the import building and we contractor design portioned all the timber. So we didn't actually design anything past stage 4, which is our technical design stage in the UK. And they were responsible for the design of all of the members and all of the connections in the final case. On the export building, we wanted to keep that design, but we still weren't really confident in connections, so we kept those with the contractor on this building. And I learned some lessons on this. So you've got a connection. This is a fin plate connection with dowels. These fin plates can pre-screw to the columns. And what you've got to allow for with a steel connector plate like that, the steel, I think, well, if instrumescent painted, which this obviously isn't because it's inside, but if it was on a bearing plate on the bottom, and it was, that instrumescent paint starts working at about 600 degrees. Timber chars at about 450 degrees. So with a route in with the steel connector plate, you can start charring from the inside, which you've got a design for as well. So everything needed to be plugged because we didn't have the capacity to char from the inside as well on these details. So that's what you see in this image here. We've got a plug on the inside for the slot and all the plugs. This is before it was sanded down and painted, but it shows it quite well. That then gives you limitations on the size of your connection. You've got minimum screw and dowel spacings. It's a complete logistical nightmare to get your connections to work. And we realised that a lot of our members were way too thin on the export building. We had to increase them post-contract agreement, much to the client's dismay that they had to fork out for bigger beams. And that was a big lesson learned. Question here is this better? I don't know. Rotherblast, I'm not sure if you have them over here, but massive screw manufacturers, they have a really good glue product now that you can slot in a steel plate and glue around and create a super strong connection. I'm not convinced because you can't deconstruct that. It's like welding steel beams. But perhaps if you've got a moment frame or a super, hard-working structure, or fire is a massive issue in one part of the building, you could look at that solution. Gone too quick. Old Gramophone Works. We learnt all those lessons. We made all our beams big enough. Great. And then we also were hungry for more, so we decided that we were going to design the connections on this one as well. We now come up with a new challenge. Our cores, we had new RC cores threaded through the existing building. The existing building's got its stability from its massive columns, but they couldn't support another 4 stories on top of lateral wind load. And so we had new cores, which were concrete up to the above 2nd floor, and then CLT on the new timber floors. But designing the connection for those was a new challenge. Those cores had to be 120 minutes fire rated, or they had to be into 120 minute enclosures. And we designed these walls to be 200 millimeters thick, which is not that thick. So we have a series of jointed panels. We had 2 situations in the fire case. We had either a fire inside the core or a fire outside the core. And the way we finally agreed that these connections would work with the approved inspector that we have in the UK, or building control, was that we only ever considered this fire in either or situation, not both. And so there's enough screws, the screws alternate on sides, and the screws on each side can work alone in the 90-minute fire case. And they will take the full design wind load that you have to take, put on the building according to the code. For 120 minutes, these joints completely go. They're charred through completely. Every single one of these screws is gone. There's no diaphragm connection between the panels. And so we've justified those then freestanding in an accidental case in which you can take 10% of the wind load in the UK. And we got that agreed. Looking back, I'd probably have done the cores a bit differently, a bit thicker. But by the time we had net areas agreed and we'd come to this connection design situation, I didn't have the luxury of going back to the client and saying we're going to take some of your floor area away for thicker walls. We also had this problem at the junction between the concrete and the CLT. Apologies, there's a typo down there. That should be 90 minutes, not 60. But we had the char zone on the CLT, whichever side that was on. On the 90-minute situation, we have really short dowels because we had to design for that char on either side. So these are pretty often along the length of that one. And then on this one, we just couldn't get it to work. So that's 91 millimeters of charring. We then got longer dowels because we've had to put a panel of fireboard inside the stair. But the architects knew that, and they've created some sort of lighting feature out of it in the staircase, I believe. This little render's a bit wrong here. We've actually protected the edge of this plate down here with like a dry pack screed, like the cover you have to the rebar inside the wall in the same way. Buildability. On the import building, we put all those columns inside that existing building. There were tenants in there at the same time as well, on some of the floors. And it was a massive logistical challenge. VHAG were the timber suppliers and installers on that project. The columns all had to come in really small lengths, so that's a picture in their shop. Much shorter than they normally would. They'd probably go up 2 or 3 stories with them normally, but these are all single story. They had a whole series of hoists and pulleys, and they couldn't have a crane in there. There was a roof on. They had a whole system for doing this, and obviously they also had to deal with the existing structure and the tolerances and the way that the existing reinforcement inside the concrete was. So they collaborated. They installed as well, but they have an installation team, and they had that installation team on board much earlier than usual. And I think that buy-in from them, and that's a big lesson learned from me, is to get the installers as well as the suppliers involved when you've got a complicated installation like this very early on. Main contractor, the design team, we all worked together on this to make it work. The connections were all designed with extra holes in them, so that if we hit some reinforcement, we could put the resin anchor or concrete screw into a different hole. And yeah, it was a labour of love movement. Glulam and timber, obviously, it's a natural material. It moves differently to steel. On the old Gramophone Works, we've got an unbelievably complicated structural system, which, looking back, I would have liked to have simplified. But we basically, I've deleted the slabs from here so you can hopefully, I know it's just complicated, so it's still hard to see. But we had the existing column down here. We've got a steel beam cantilevering off that. That supports a glulam column, which then supports a transfer beam, which supports another column. And then over here, another glulam steel beam on this side. This is a mirror image. Supports a glulam column. And between there, we've got another transfer beam, which is complicated. And we've got curtain walling sitting on that, which has hardly any tolerance for movement. And when they asked us what the maximum deflection was going to be, we were like, what have we done? Why have we got ourselves into this mess? We ended up having to put a few steel beams in, unfortunately. But we're being honest about those and telling people about them, or not trying to hide them. So we have had to do that to control the deflections for the glazing in a couple of locations. In some locations, we used a higher grade of glulam. We used the GL32 rather than 28H. But where we couldn't get that to work, we've had to put a steel beam in on the longer spans. So yeah, that's definitely a lesson learned to avoid in future. And then moisture. I mean, I touched on the Accoya and the brackets earlier. We also obviously set up glulam columns from ground floor level. These particular ones had a super high raised floor, which is why they're so tall. I think it's normally only about 150 mil that you have to sit them up. But we've also got into the habit now of asking the timber suppliers to provide a water management plan at the outset of the project. So we know how they're going to temporarily drain off the water in the temporary case, and how they're going to manage the main contractor to continue to do that until the envelope's completely watertight. And that's something that's become one of the first things that we talk about as soon as the contractor's on board. Yes. So this has kind of led us on to looking into innovations. This is something I've been doing with my research group for a long time now. And we were looking at, the fact that at the moment, you have a glulam beam, and in both of those projects that I've just talked about, you've got CLT on top, and you design that beam on its own, and you design the CLT just as a weight on top of it, but the CLT has capacity. And so it could also help the beam. It may be spanning in one direction, but the central layers are in the strong direction to work compositely with it. There are products out there which do this, like the rib slabs, but they're made in factory, glued, homogeneous, and the ribs are at very close centres. What we'd like to do is main secondary beams use the composite benefit from screwing and get the structural zones down, increase clear heights, or increase the M&E zone. And so what we did some screw testing. We thought the weak link would be the screws, because we didn't want to glue this because you can't bring it to site so easily. So we wanted to just make it work with screws, because we're putting screws in anyway, so they've got a lot of capacity. There's nothing in the Eurocode that tells you how to do this. CLT isn't in the Eurocode. I don't think it's in the codes here either at the moment. We use these for our warranties. We use the European technical approvals as a product. The only equation that the Eurocode has is this, and looks a bit complicated, but actually it's just really over the top. And then they just put a random 2/3 in. Nobody knows why. So it's even more conservative. And so we did a test. We did a couple of tests, actually. And the screws never failed. The glulam failed at the bottom. So it was a tensile failure. And this graph down here is quite... oh, no. Sorry. That's a bit dramatic. Yes, so if you design your glulam beam, just as we have had to on our project so far with just the weight of the CLT on top. You get the red line. This is how much deflection you would get as your load increases. If you use that equation over there, you get the green line, so you get a bit of an improvement. If that was a homogeneous T, all of the same, exactly the same material, you get the yellow line, and the blue line was our test results. So we don't quite get the full effect, but you definitely get a massive benefit on what we're designing for at the moment. And what we found was actually the limiting factor was actually getting through the layers of CLT and mobilizing all of the effective width that you have there. And we're currently trying to model this in 3D finite element analysis to see what the rule is and where we can get to. But I was talking to Justin earlier. I think he's got some amazing new glue that means it's much more homogeneous than before. So I'm quite excited about learning a bit more about that, hopefully later this afternoon. And so this is the only slide I've got on this, but we're looking into everything because we want to learn more. The other thing on this structural zones and squeezing your M&E and your structural zone, your clear heights, minimizing cladding costs and cladding carbon costs, is also creating a zone for services. At the moment, you can get a hole through a glulam beam, but it's pretty small, nothing like you can get through a steel beam. And so we're looking into ways of improving that, inserting steel plates, inserting LVL inside a glulam beam, or a hardwood composite of some sort. Screw reinforcement, which is already out there and you can design for, but even more improved screw reinforcement around openings. We're looking into all of those avenues. We're looking at vibration. We actually did a vibration test on this as well, and on our old Gramophone project, we're using justification through the composite action and the tests that we did to explain some of the response factors and the frequencies on there. What else are we looking into? Connections. Oh, I was really excited about the last talk to talk about the nodes with LVL. We've been looking at that as well. Obviously the acoustics, and we're looking at grid studies as well, where what's the best grid for CLT. I mean, all the projects we've got in planning at the moment kind of have just one main beam line and the CLT spanning as far as possible, because that's the most efficient way, carbon and cost-wise, we've found so far. And thank you. That's it.
Thank you, Kelly. One thing which I think we all can agree on and have experience with, to one extent or another, is the way in which working across the families of timberwood projects and products compels integrated design approaches, compels collaboration, compels working across disciplines, compels deeper knowledge of ecologies and biological systems. And in many ways, it's what's extremely encouraging within an academic environment, and I think equally encouraging in the professional environment, is the way in which architecture and engineering are working hand in hand. I believe much more perhaps than ever before. We certainly see it here at this university, where for the first time in many years, coursework in the College of Engineering in engineered timber has returned to the curriculum, and there's a wonderful set of outreaches occurring between our school and the College of Engineering. So what you're doing, what Tanya's doing, what others are doing is utterly admirable, and we can't thank you enough for the outreach that you're making as much as I hope all of us are making towards engineering. We move forward. Our last presentation in this graduate seminar over the last day and a half is that of Erin Dorf of Snøhetta. Erin Dorf is a director and senior architect at Snøhetta with over 12 years in the New York office, overseeing projects including the National September 11th Museum Pavilion in New York, the San Francisco Museum of Modern Art expansion, Harvard House Zero, the Blaisdell Cultural Center redevelopment in Honolulu, and the Joslin Art Museum expansion in Omaha, among others. Erin looks after Snøhetta's North American powerhouse work, a body of projects and partnerships that follow Norway's strictest sustainability practices for zero-emission buildings by promoting ultra-low energy use, zero or positive emissions, and healthy materials. The first North American project by members of the Powerhouse team, House Zero, is a renovated office space and headquarters for Harvard's Center for Green Buildings and Cities, a tiny project with huge ambitions. Please welcome Erin Dorf.
Thank you. Hi, everybody. Thanks for coming, or thanks for staying, I guess. We're at the bitter end, almost. Well, the sweet end. I was kind of thinking this morning about how I got here, and it takes me back to 1998. That's when I met Peter. And maybe it comes back to just earlier than that, when the semester before I met Peter, who taught a studio at the University of Virginia. When I was there, I went abroad. I studied that semester in Copenhagen. And at the University of Virginia, they tell you not to do that. They basically say, everything you need to learn is here. We know what we're doing. You don't need to go to Europe and learn things. What do they have that we don't have? And so they discourage you from going abroad and learning new things. And one of the ways that they discourage you is that back then in the 90s, they had the only computer class that was available for like 3D modeling the same semester you go abroad. So basically, if you go abroad, you don't get to learn computers. And so that's what they hold over your head. And so I said, well, forget it. I'm probably going to get it anyway somewhere along the line. And I went. And when I went, it opened up my entire world to Scandinavian architecture in a first-person kind of way that I couldn't have imagined before. And of course, that completely opened up my eyes to the possibilities of wooden architecture, of natural materials in architecture. And so, indirectly, that's probably how I got here today. Somewhat more directly, I got here because I met Peter the next semester when I come back, and here's this young, dashing guy who has this kind of quirky accent because he'd been living in Finland for so long. That somehow changed him into a Finnish person. And it was this kind of, it continued my education into sort of the world outside of American construction, the world outside of design that I had known and been studying in college. And that really, that opened up another door for me. So in addition to bringing me here, I can thank you for that. Maybe long overdue. So I promise that I will talk about wood today, but I think that one of the reasons why I thought this was so interesting was that, of course, we use a lot of wood in our work. Natural materials are fundamental to how we approach everything. But it's, in my opinion, part of a much bigger project, which is the reason to use things and promote new systems in wood and new ways of thinking about wood ultimately comes back to sustainability. And sustainability has been a word that's been around a long time, but the push to become more sustainable couldn't be more critical than ever. I mean, it's my first image was not a beautiful landscape in New Zealand nor Portland. It's to think about, a week and a half or 2 weeks ago when I was at the climate strike in New York with my daughter. And I would think about how we got here from the almost, just the first days of industrial history in the UK. This is essentially the cradle of the climate crisis. And so, the practices that came out of this culture and the industrial society that evolved afterwards into what we know today, it affects everything we know and everything we do. There are some numbers that are kind of becoming more well-known, and I think that's good. I think, you can basically, in all of the, Architecture 2030, Paris agreements, like when you look through all of the, the sort of mission-driven culture of sustainability and how to make improvements in what we're doing in our practices, ultimately, you can see, our ability to impact things is huge. We have this is a higher number than people used to talk about just about 40%, and now we're getting towards 50% of the world's emissions comes from the building sector, and within that, there's two huge ways to affect how we work. One is building operations. Obviously, about almost 3/4 of the pie is how we understand buildings, how they operate, and how to approach things from an ultra-low energy use perspective. The other is the materials we use, the way the materials get to the site, the way the materials are downcycled after they're on site. All of these things obviously have carbon embedded in it. And so when I said I'm going to talk about wood, I will talk about wood, of course, and I think that it's intimately connected to everything that we're doing, especially things that are being driven by sustainability measures. But the part about it that is critical is that, wood is such an important tool in the carbon replacement toolkit. It can do many things. I don't think we've personally scratched the surface of how far we can take wood in terms of replacing other building materials. But there are some ways that we have started internally. There are ways that we look at using wood in projects. And so I thought I would start by maybe showing you a few different things. One is that we have a sort of body of knowledge within our office that we call loosely the powerhouse projects. These are generally projects that follow the zero-emission building standards that come out of Norway. And when you look at net zero, zero-emission buildings, all of those things, there's an array of slightly different titles and systems that different jurisdictions in different places around the world follow. It's pretty confusing when you actually start comparing them and trying to understand who's doing what compares to what. And so I'm going to explain a little bit about the way that we see those comparisons through our work. And so the powerhouse projects essentially have grown out of a series of partnerships that we started in Norway, and they've started to become exported abroad. Those partnerships are probably close to what you would call integrated design today. So it's essentially a kind of cross-platform interdisciplinary team. It includes owners, it includes developers, it includes designers. We're usually the design lead on this team. It includes engineers, manufacturers, contractors, and operators of buildings. And so we, as a practice, we've, of course, been around now exactly 30 years. About a week ago, that was in 1989 is when we originally won the Alexander Library competition. That was when the sort of notification came through. And so really it was a week ago that we celebrated our 30th anniversary as a company, and we've been working around the world for a while now, since it was actually a collection of people that won that competition. Not just Norwegians, there were people in LA as well. And so it started out as an international office. It has stayed an international office. We have offices in New York and Oslo and San Francisco, Paris now, Innsbruck, Hong Kong, Adelaide. Some are big and some are small. New York and Oslo are the two biggest. But our work has of course been occurring around the world. But what's the more interesting thing for me and how it leads to the future is how our powerhouse work can become something that's actually leading the practice as opposed to just a kind of portion of it. And it is starting to inform all of the projects that we do. The things that follow the zero-emission building standards essentially and I'll explain how it works, kind of what this perspective is on emissions from a Norway perspective in a minute. But essentially, you have to account for all of your carbon, all of your emissions, both in terms of operational energy, in terms of materials and construction, and there are different levels within that system. But the projects that are in green here are the sort of first powerhouse projects. Now, about, I would say, a third are now built. There's now probably 5 or 6 more in design right now. And what I'll eventually get to is the first project that we completed here for Harvard. And I see somebody from that area right now. So maybe I'm not the only one who's seen it, but we are now also doing design and research development for new projects in the US. And so hopefully there'll be more to talk about in future symposia. But the important thing to think about with the Powerhouse is that this is a huge collection of different groups. Not all of them are technically a part of the Powerhouse group, but they're all different different parts of the building sector, whether it's research, whether it's modeling, whether it's manufacturing, whether it's construction, that get together and essentially we run workshops as we start projects, and the workshops have everybody in them. And those workshops, and so now when we have meetings, everyone is obsessed with efficiency, and so no one wants to be in a meeting that they're not supposed to be in. But it's actually kind of important, especially in the beginning, that everybody is in every meeting, because there are important perspectives that come from all corners of this process for us. And so, yes, we work on these projects. We work on some of the bigger projects that get a little bit more notoriety. I've been lucky enough to work on a couple of them. I spent my first 7 years in the office working on this project at Ground Zero. And then I spent the next 6 years working on this project until it was completed a couple of years ago. And they're fascinating projects, and they're rewarding in many ways. But the smaller projects that are actually trying to push the limits of what we're doing in terms of sustainability and thinking about reducing carbon and emissions, these are actually more rewarding projects. And I personally think about how I can do more of these going forward. And so some of the ones that, these have now actually all been completed at the time that I made this slide, probably when I presented it a couple of years ago. Some of them were not. And I'll talk a little bit about all of them. This is an office renovation, really just outside of Oslo. It was completed probably about 5 years ago. This is a pilot house for a developer for, it's essentially a kind of a zero carbon spec house. And so this is available for owners to purchase and adapt. This is a Montessori school that was just opened up about 2 years ago, and this literally opened within the last month, I think, officially. This is the northernmost powerhouse project. It's the northernmost energy positive building, I believe, in the world. I mean, it's pretty much at the Arctic Circle, and so making that work in terms of something that's solar driven is a pretty interesting prospect. And so how we get there is, there's a lot of pieces to the puzzle, right? So there's, to get to something called net zero, and we'll talk about why that can mean different things in a minute, you have to look at so many different aspects of the kind of design and building and operations cycle, both from the perspective of lowering energy as much as you possibly can, and this is really critical in zero emission buildings, maybe a little more so than your traditional net zero projects. Thinking about the equipment that goes in the building, of course, making sure that you use efficient equipment, making sure that the people in the building are trained to use the equipment efficiently. It's actually pretty important and gets overlooked quite a bit. That affects energy behavior and educating the users in the space. And then commissioning is pretty critical. Some projects, like the project at Harvard, is basically being commissioned slowly over a year. It has to go through all the seasons before we can even begin to test and do post-occupancy research on it. And then optimization once it's going. And then, of course, what I like about this diagram is that it makes this, it minimizes renewable energy solutions, not because they're not important, but because they should not be driving the project. The project should be fit to the small amount of renewable energy that you can live with on site. When I mentioned that there's this kind of somewhat integrated process, you know, the way that we see the powerhouse work is a little different from your traditional kind of design and documentation curve, this sort of like effort curve. You know, the traditional way of doing it is really more out here, you know, this gray curve, where as you begin projects and you get into the concept, you know, you're slowly moving through and building towards construction documentation, CDs, where the lion's share of the work, the lion's share of the fee, the lion's share of the knowledge is being developed in the project. What's really interesting about the Powerhouse projects, and certainly was the case on the Harvard project, is that there is a tremendous amount of CD level work that goes into the concept design. So on that project, for instance, we were doing computational fluid design in concept in order to be able to test the ideas that we were eventually going to implement. And if they didn't work in concept design, we just threw them out. They weren't going to be a part of the project. So it really does push things forward. And the other thing that it does, and I think this should be important for any project, but is critical for these kinds of projects, especially where you have an integrated team, you have contractors on board, you're getting pre-construction knowledge, is that subcontractors are in the meetings here. And usually when you work with a contractor and you're getting pre-construction, and this is a tip for later when you all are in offices, pre-construction still isn't pre-construction. You're not really getting a lot of pre-construction knowledge. You're not talking to subs, you're talking to contractors on their pre-construction teams. The pre-construction teams are not the guys in the field. They do know a lot, but they're not actually the ones who know how they're going to build each project. And so what you're getting is a kind of light version when you get pre-construction information from a contractor that doesn't actually always get implemented later in the field. But if you can push the contractor, if they're a part of the team, actively in the beginning, and push them to get subcontractors in the room, the actual people who are going to be, you know, fitting the pipes together, you're getting knowledge that directly translates from whatever you draw to whatever gets built, because those should be the same people that are actually in the building later. So when I was talking about the differences between different sort of net zero enterprises, I think that one of the big ways to think about the differences between Norway and North America, just as a point of comparison, is to think about the differences between the way the net zero the enterprise in North America thinks about things through the lens of energy, principally, and then really the focus in Norway is more on emissions, and that has an interesting effect. So net zero has a lot of, again, classifications, net zero energy buildings, and there's a number of names for it in the US and North America, but essentially they allow you to be net zero can mean many things here. You can zero out your operational energy, or you can go beyond that. But what's interesting about the system here is that you start with the idea that you can zero out your operational energy in a building on site, but then there are loopholes. So if you can't do it in your building footprint, you can do it on site. So that does not incentivize you to have an ultra low energy building, because that just says that, hey, look, I have a site, I can add more renewable energy all around my site, whether it's PVs or other, turbines, geothermal, whatever it is. But it doesn't incentivize you to keep your energy use low. All it does is it tells you, you look at what you're using in your building, and then you size your renewables to fit your what your building or your project is using. So that's great. You're balancing out your use, but you're not keeping your use low. There are more loopholes, right? You can actually now go look at buying. You can put your renewables off-site. You can go beyond the site boundary. That goes even further in terms of not incentivizing you to have low energy use on site. And then you can go a step further. Instead of installing renewables, you can just buy them. And who's to say those renewables get sold once? An energy company can tell you that they're selling you renewables, and you can go balance out your project and tell everyone it's net zero, but they're credits, they're imaginary. It's like the money in our bank account. They're just numbers on a screen. We don't really know what's happening. So there's not an incentive to keep energy use low. And as you look farther and farther out from the site, there's no guarantee that you're really balancing out your energy use. The biggest difference is pretty simple. And so in zero emission building in Norway, you've got to do it in your footprint. And so whatever your footprint is, however small your building is, and even more importantly, if you're doing a renovation, you have some constraints that you have to live with. And so you're not sizing your renewables to meet the demands of the building energy, or the energy your building wants to use. You're sizing the building energy use to meet whatever renewables you can fit onto that footprint. And that has a huge impact in terms of your incentives. So what happens in Norway is that they, like every system, there is a series of kind of grades to that system. And they go from less intense to more intense. There are the non-zero emission building projects. And then moving quickly, you get to the sort of ZEB-O, which just covers operations. This is the most traditionally aligned with net zero building in the US or in North America. Most net zero projects just look to balance out operations. And as we just discussed a minute ago, how you balance them out can happen a lot of different ways. So the story can really be flexible. But it's not as flexible here. So then the next level of projects is that you balance out operations, and then you add in materials, but it's not forcing you yet to account for the equipment in the building, the user loads, the plug loads. Those can be pretty tough. They can actually add quite a bit of extra energy to the building, which is why this category actually allows you to subtract it. And it's still doing quite a bit. That you're dealing with the embodied carbon in the embodied energy in your materials, which is a big deal. The next one, of course, essentially it's the same, but you add the plug loads back in. So now you have building systems, you have user plug loads, and you have materials. The next one now accounts for all of that plus the construction cycle. So all the energy that goes into construction is accounted for. And then the last one, the hardest to achieve, includes end of life, recycling energy, and essentially this is cradle to grave. So some of the projects, and now there are more since actually we started, made this little diagram, fall in different areas of the spectrum. All of them go sort of kind of beyond the just operations level of the ZEB scale. And so, some of them are not as clean as others. Maybe a project actually goes all the way out to a ZEB-COM in some cases, but actually, we subtract plug loads. There are different ways to think about how to essentially balance out your energy and your carbon over the lifespan of a project, whether you're measuring to 60 years, sometimes certain building types you measure to 100 years. It kind of depends on the building type as well. So to begin with, I wanted to just walk you through one of these projects. This was the first one that was completed, the Powerhouse Shareable project. This is an office retrofit. These are older buildings, 1960s, pretty inefficient construction. This is just outside of Oslo, and it's actually a campus. There's multiple buildings on campus. And the project started out as a retrofit of one of the buildings on campus, and eventually it'll roll out to all of the buildings on campus. This is what you get on the inside. It's about what you would expect. It's mechanical systems, that are all above the ceiling. It's small windows that don't allow for a lot of daylight. The Powerhouse projects, in order to reach ultra-low energy use goals, you have one tool or another. They have a kind of range of tools to get there. So you have to increase daylight. You have to essentially try to make the building more passive, but you don't always have to count on being fully passive, because in every building type, that's not actually possible. So we, in all of these projects, in this one in particular, run through a series of calculations in terms of, what are the materials account for in terms of their CO2 emissions? What's the energy production on site? Are we balancing those things? And so those get looked at a pretty fine grain level. The building, for this example, we start to look at the power density as well. So, these are different case studies of different types of office building structures and what their power density is in kilowatt hours per meter squared per year. So the target for this building is pretty aggressive. It's 35 kilowatt hours per meter squared per year. And so you can see, I mean, we're looking at reducing the energy to a quarter, an eighth, or sometimes even more of what a traditional building will use. Then we also have to think about how the building, how this energy use plays out over time, especially compared to, you know, the kind of typical case building. This kind of graph shows essentially, you know, the more energy used, the more you dig a hole. And so this is showing a typical building, energy use over time. This goes out 60 years, and it assumes that there's no renewables, so you're just using more energy over time, and you never bounce back. In this case, the building, the projected building energy use assumes the renewables that are planned for the project. And so, of course, you have an initial amount of energy expended in the first years that accounts for the energy that goes into the project, the embodied energy in the materials, et cetera. But the renewable energy slowly pulls you out of the hole until you're in the positive. And so all of these projects have to look at how that's possible. So that office, you know, the design premise of that office space that you saw before was that you take out all the ceilings, you expose the thermal mass that's above the ceilings of the concrete slab. You know, you use all recycled materials wherever you can. So wood. I'll point out some materials that were used on the facade in a second. For acoustics, is recycled plastic materials that are baffles that go around the space. You know, cork flooring, recycled butcher block floor. And so essentially creating a light-filled space. The core has lighting and the core has air, but there's very little of both of those things throughout, and there's no air anywhere else throughout the rest of the floor area. There's just natural ventilation at the facade, and there's low-velocity displacement ventilation coming from the core. And then there's essentially a kind of stack effect that goes through the stairwell. So all of those ducts are now gone. It allows us to essentially not only kind of, you know, create productive holes in the floor slab that weren't there before, but to make them useful for the energy performance of the building, but also to create a design opportunity as well. Again, the natural ventilation relies on a certain amount of passive activity, so being able to passively move air through acoustic vents that are above the ceiling. And then, you know, getting back to the facade, thinking about ways to, of course, treat the wood, you know, by burning it and making it, you know, there's lots of different ways to do this. Of course, this is, you know, an old method used in Japan and other places where, you know, you can make the wood virtually impervious to weathering for a much longer period of time. You have to add energy to do that, but it's interesting the way it balances out over a long period of time, because one thing about sustainability is that, you know, I think somebody said it today, sustainability is about using less. That's absolutely true. But sustainability is also about making things that last much longer. And so if you can take something that has a certain lifespan and make it last 4 times as long, that's very good. And so we've gone from these aluminum office buildings or aluminum clad office buildings to this you know, carbonized wood facade office building. I'll try to move through these pretty fast, but the next project that we completed was this pilot house, much more aggressive. It accounted for construction, operations, and materials. And so this was kind of built in outside of a housing development as a way to test out the materials, test out and calculate all of the energy use. The developer was the client, and they're a part of the Powerhouse Alliance that is, you know, this kind of cross-disciplinary group. So they were, of course, very interested in promoting this kind of building. And so it's a single-family house. It's got some interesting there's interesting ways of using wood in the house, of course. We've some facades that integrate both brick and which is recycled, and then also this kind of arranged log, kind of like the chopped wood wall, and then again, you know, flame-treated wood for the cladding, and there's recycled wood furniture, and in the ceilings as well. So this, again, I won't stay too long on these projects. I want to move through to the end where we talk a little bit about the project that we finished recently at Harvard. And this is the Powerhouse Montessori School, a little less ambitious than the pilot house, but more ambitious than the Cherbourg project. This has just opened recently. It's in its operational testing mode, although it's open. And the other thing you'll notice about some of these projects is all of them, especially the ones in the northern climates, they all pretty much have to come up with a fundamentally geometric way to address the solar issue, because often, and especially in the northernmost projects, you have to maximize your surface area as much as possible, and then the sun angles, of course, in the Arctic Circle are much different than they are down here. And so this is not quite that far north, but and it's got a pretty steep angle, but quite often the solar renewable energy aspect is becomes an aesthetic driver, not so much for the equipment, but just for how we orient to the sun and how we establish a large surface area. This is the project that's opened just recently. It is probably the least ambitious on the scale, but it's the biggest. It's about 180,000 square feet. It's just recently opened. This is in Trondheim. It's connected to the rail station here. It produces twice as much energy as it consumes. It actually has enough extra energy in storage that it can basically supply the building through the many months where there's very little sun. It also can supply the city around it. It gives back to the grid. So you can see that the roof is essentially a PV array, and it was maximized. We try to maximize the angle and the surface area, but with the other constraint that you need to get light into the middle of the building through a light well. And so that was, given the footprint, that was optimized to try to reduce the floor depths. And so this project is really just being in the beginning of sort of its testing phase. And so it kind of brings me back to why I'm here. So I think that kind of at least sets the stage for some of the projects that we're working on that are really focused on reducing emissions in the building industry. The projects that I think get a lot of attention quite often are almost all projects that use a tremendous amount of wood, not necessarily in a kind of hyper forward-thinking way or inventive way structurally. Sometimes it's about creating a different way to use, wood that kind of fits the use. So whether it's these, this wild reindeer pavilion in Norway, this actually looks at the mountain of Snøhetta that the office is named after. These have kind of massive timber pieces that are all CNC milled. They were kind of brought to a shipbuilder shop who could do it. So the front and the back is treated. I'm not actually sure what the treatment process is on the back, but it's essentially weatherized. This is kind of a warming hut, and it's the place that you can see the last wild reindeer in Norway. And a project that just opened up recently, Calgary Public Library. This is a project that connects two parts of the city, a pretty underused part, and kind of, I don't want to say, it kind of like a pretty sort of spotty part of the urban fabric that's full of old saloons and there's a new development that's just beyond this building. This one sits right in between, right on top of a train station, or a rail line. Whoops. Oh, that's a sensitive trigger here. Right on top of a rail line. So that has always been a kind of boundary across the city, across which it was difficult to traverse. But this building has created a way to move up and over that. It takes advantage of western red cedar forest. There's a huge abundance, of course, in that part of Canada. Interesting going through the process of figuring out how to make sure that it can bend and sort of curve in both directions. Using it on the inside as well as both an acoustic treatment and aesthetic treatment, a way to warm up the light in the space. And so this is something that we're more familiar with doing, of course. And then it starts to evolve as well into other projects that we're now getting into. This is a project that we started with Sidewalk Labs. Sidewalk Labs is very interesting. Of course, that some people may know they're a part of Google, and they are highly invested in the development of cities. And they have created a manual for CLT construction, for themselves and for the industry. And they essentially asked a series of architecture offices to come in, look at a different part of this site on Quayside in Toronto, and essentially kind of take their system and push it as hard as you can and try to see what kind of design can be developed at a master planning level. So these are pretty early days in this project, but you know, we both use the pretty standard format of their system to kind of work through tower ideas for residential, but then when it came to the kind of the more public realm and the office spaces that are here, we pushed harder on their system to kind of test the spans and you know, to get out of the grid system that their book essentially has set up. And that was really with their blessing to see what you can do. And of course, it's kind of engineered at the master planning level, so it's so early as to you know, not really have to figure out yet quite how all the details come together. And just seeing a little bit today about how complicated that gets, it gives you kind of a respect for, you know, going from a right angle to a 30-degree angle could actually have an implication that you're not ready for. You know, that could actually that could be another month-long design problem. But it's something that that we got excited about. They got excited about how far we pushed their system. And so there's kind of discussions now about where this goes. And so I think it's an interesting kind of stepping off point. It relates to some of the things we heard today. It's, of course, much more speculative than real. And so there's a lot of, I have a lot of respect for all of the projects that actually push it into reality. Which kind of brings me to this project. This was a project we started in, I want to say 2010 or 11, and we the way it came about was we met with the director of the Center for Green Buildings and Cities, who has been doing he's been researching Scandinavian sustainability in general through projects and through academic work. And they were occupying for a year or two already this building that's on Sumner Road behind the GSD at Harvard. If you've ever been there before, so it's sort of one block behind. It's a small wood frame house. It was built in, I think, about 1925. It's in a historic district, so that there's a mid-Cambridge historic district that it's not the most stringent in Cambridge, but it definitely. You have to go and review it in front of a historic board, and you can't make changes that essentially they can't live with. And so, you know, they care a lot about things like windows. They care a lot about the sort of fabric of anything that you're going to renovate. The roof pitches are a big deal. And so one of the premises of the project was that we can do something that can radically transform a building like this to run on almost no energy, in order to actually balance out things like carbon for, you know, over the lifespan of the building, to produce twice as much energy as it requires on a day-to-day basis. So there's a lot of things you have to do to a structure like this to make that happen. Renovation projects are kind of a particularly interesting niche in the zero-emission building industry, and there's not a lot of it because it's harder to make those things happen. And so the director of the center came to us just to kind of present what his PhD students had been working on. They had kind of a huge menu of ways of operating on this house in particular, how to transform it to be basically, you know, to run on almost no energy. It wasn't a cohesive set of plans. It was just a lot of things you could do to the house. And so we were contacted and brought together with the director and reviewed all of the work that they did, and then essentially they asked us to kind of lightly comment, but then quickly get into a project with him to actually make this real. And so the Center for Green Buildings and Cities is a fairly new center for Harvard University, and it's essentially you know, for lack of a better word, it's kind of a think tank. It promotes sustainability, but it promotes design-centric sustainability, but very much through the world of simulation, so that you can empirically test things in the world of computer simulation air velocity, temperature, daylighting, all of these things, so that you can actually, you can be ultra sustainable before you ever build anything, and you can try to test out your ideas all the way to basically the end of the project before construction starts. And so it's a pretty interesting center, what they're doing. They have a series of people in that center that have different specialties within the different simulation worlds. And so we were able to work with them as part of our, almost like a consulting team. They had somebody who could do, wind modeling. They had somebody who could do daylight modeling. And so we had a very small team of an architecture office, and we work with an engineering team that actually is a part of Skanska, who's a construction firm that's out of Sweden, but they build all over the world. They have a very small engineering team within their office that actually specializes in the zero-emission buildings. And what they do is kind of really outside the box, and we all work together as one team to test everything. And so the goals for the project were really aggressive, and to our knowledge, at least at that time, had never been done before. So essentially to zero out the energy that you needed for heating and cooling and electrical needs, so that you didn't actually need to pay for any energy at all or buy any energy from the grid. Zero mechanical ventilation, so it had to be 100% naturally ventilated on site, which in Boston is a challenge. And the winter is maybe a challenge, but actually it's harder in the summer when you have high humidity. Zero electric lighting needed during daylight hours, so that means 100% daylight autonomy. It does assume that sometimes you're going to have cloudy days, and so sometimes the lights may have to come on, but essentially if you don't have ultra cloudy day, you don't need any lights on. And then we had to zero out zero out or have positive carbon emissions throughout the project's life cycle. So how we looked at the project from the early days was really was about lowering the energy use, because essentially we had a tiny footprint of this building. The tiny footprint sets the parameters of how much energy the renewable energy that the project can make. And the other part that made it tricky is that we had really bad roof orientation, so that just adding solar was going to give us suboptimal renewable production. So we had to find a way to really push the energy use low. And so if you compare, for instance, kind of a typical wood frame home in the Northeast climates, it uses around, and this is I'm using the kind of metric unit, so I wasn't able to convert it very easily. The average house uses around 232 kilowatt hours per meter squared per year. A passive house, and again, there are many types of passive houses, but they typically cut that energy use in half, which is amazing. But they do it in an interesting way. A passive house, one of the kind of signatures of a passive house is a fairly over-insulated envelope. And one of the things that I'll bring up in a minute is the problem with over-insulated envelopes is that they use a tremendous amount of carbon to do that. I mean, most insulation products are petroleum-based, mineral wools, foam boards, all of those things. And so there are newer products on the market. They are hard to use for reasons I'll get into in a minute, but they're not impossible to use. But basically, to reach the really intense insulation goals for a passive house, you have to over-insulate pretty consistently. And then, of course, it has to have air tightness and has a certain set of mechanical parameters it has to follow. The targeted energy goals for house zero are trying to cut that into a quarter. So essentially, we're looking at trying to be almost a tenth of an average house in terms of energy density use, which is really, really aggressive. And we'll know if we can hit those targets when we kind of go through a whole year of testing, and we're not quite through it yet. This is an early rendering. It kind of shows the house not so far from where we ended up. It also shows basement expansion that is sort of phase 2 of the project, and we hope one day we'll be able to do that. Well, we built the project actually ready to accept the expansion, so there's already a tunnel below ground that's half built. And so this is essentially an office for 25 people, and they want to be able to expand to another 10 people or so in the basement expansion space. And so what's really interesting is that we're working with, we're comparing to energy targets for a single family house in terms of the amount of power density that the single family house uses. Whereas we're trying to do it with 20 to 25 people in the house using it at all times, which is a challenge. This is a diagram that the center kind of came up with, and it's kind of an easy way to sort of describe at a very basic level the differences. You know, a common approach is very systems-based. Every system, the cooling system, the heating system, everything depends on a machine. And it's not just the forced air system, but it's also the kind of the fan system to kind of spread the forced air system throughout a space. You know, it's incredibly energy intensive. And that's not to say that house here has no machinery. It does have a minimal amount of machinery, but it's subtracted quite a bit. There's no ducting in the house. It's all naturally ventilated. And it really just has a geothermal system. That's kind of the primary system in the house. This was kind of the project as it developed. A little later on, we started to figure out how this mix of systems could actually get to that low energy use. And the key part, the wood part of this equation is really important, because when you have a really small footprint and you can't make a lot of energy, you have to make sure your energy production or your energy use is really low. But if you're also trying to zero out your carbon for 60 years or 100 years or whatever your range of calculations is, you pretty much have to use ultra low carbon materials, which means a fair amount of wood, and you have to be inventive about the way that you use wood. Or else you're never going to make it all calc out. So the natural ventilation systems use the windows. The windows have an automated light and a manual light. It uses a glass and brick solar vent to induce buoyancy-driven ventilation that actually just really ventilates for the high occupancy basement spaces. So it's designed to take both the renovated basement and a new basement space. The windows were all enlarged, and we added new windows as well, which was interesting as part of the restructuring of the house. The house now had to meet office loading, which was much higher. Well, modern day office loading is like, you know, several steps above 1920s residential loading. So we had to do quite a bit of restructuring of the house by adding a lot of engineered lumber, and no steel was allowed. And so we improved the envelope, but we had to do it in a particular way that used almost zero petroleum-based insulation. So we used wood fiber-based insulations. We used recycled denim insulations. The other thing we had to do, which kind of goes against the carbon story in a way, but allowed us to come back again with ultimately a net improvement, which we had to add a lot of mass to the house. The house, as a wood frame house, only has mass in the basement. And so we actually had to pour concrete slabs on top of the existing wood frame floors. We had to restructure the wood frame floors by sistering all the joists, which became kind of a cool aesthetic and acoustic tool on the inside of the house. And while most optimally, I would have loved to have done this in stone, it didn't fall in the budget, but that would be probably the even better way to add a lot of mass to the house, but keep the carbon even lower. So we had to account for that a little bit of that carbon sink. And then we use, we have a couple of geothermal wells that cycle low heat and low cool temperatures. It's ground coupled, so basically during the winter the water cycles down. It's a closed loop system. It gets warmer water but not hot water, and circulates it all throughout the slabs. And then, of course, we had to upgrade the house, make it accessible, add accessible ramps, and even an elevator. So those kinds of things are not something a house has to do. But the point is that we're testing out more things than a house needs to do to see what it can all do. The house is highly monitored. It has sensors. It has many sensors on every surface. There are sensors. There are external sensors. There are internal sensors. There's velocity, temperature, light. There's surface temperatures in the room, right on the painted surface, right behind the wall surface, high and low. And so actually the house is subject to an ongoing CFD model that's live, that they're building constantly. So it's kind of it's an interesting way to test real time what the house is doing. The house is actually a pretty good case study, because as far as houses go, it's pretty geometrically simple. It has a fairly north-south orientation. So it reduces some of the variables. The window systems, we had to use a pretty heavy-duty German window system. that could meet our energy targets for thermal conductance. The lower light is the manual light, so during the summer you can pop it open if you need to. The automated light is the one above. That's not to say that it doesn't get used during the summer. It does, but essentially it also gets used in the winter as a draft shelf so that it can just kind of crack open and it pulses. And so it runs through automated motor system that's Danish that was integrated into this system. And so they actually ended up doing all of the manufacturer ended up doing all the CFD modeling to make sure that the natural ventilation worked throughout the house. Couple more minutes, okay. And so we have the solar chimney, which is recycled brick and glass, and then of course we kind of get to the daylighting, which is different shaped collars for all the different windows. So I'm going to go through this pretty quickly, but in terms of the carbon replacement, you'll see essentially wood became the principal tool at each stage. So we have structural steel, which we had to supply, we had to replace with wood and engineered lumber, concrete retaining walls, heavy timber. So we got rid of all our retaining walls on site and used kind of heavy timber retaining walls structures. In some cases, stone and masonry, and then where we had to use concrete, we used ultra-high Portland cement replacement like slag at 80%. Insulation, we used recycled wood and textile products. That can be difficult as well because of the weather issues. And then photovoltaics, you have to minimize the photovoltaics that you use because they use a lot of energy to make and a lot of carbon to make. So you have to keep it pretty minimal and lean. We used a recycled wood fiber product for the building insulation. The main exterior wall insulation, you can't use it below grade, but you can use it above grade. And inside the house, we had a denim product. When we got to the kind of site walls, they were a pretty cool opportunity to sort of use all of these, the kind of traditional garden wall system. What we found out is that no engineers actually want to engineer this. And so even our building engineer wouldn't touch it. It's not a system that ever falls in their normal scopes. So we had to do a design build with a landscape construction company. And so it kind of gives us, we have light wells and stairwells around the house that are all built instead of out of concrete. They're all done with kind of heavy timber garden wall construction. I'll go through this pretty quickly. The carbon balance, basically, you can see we ended up using more or making more energy than we need. That accounted for materials. When you take the materials away, we make twice as much energy as we use. And then we kind of get to other performative aspects in the house. The acoustics in the house are all sort of controlled through the stairwell as well as the heavier mass floors. We worked with students at the GSD. In their CNC lab, we basically kind of designed, and then they kind of worked out a lot of the constructability and actually milled all the panels for the stairwells. So the stairwell that goes up was kind of this hyper-custom acoustic chamber that really does work to knock down all of the acoustics or all the noise in the house. All the material research that went into this, we got to work with the Office for Sustainability at the university. It was interesting to go through all the different plywood products to understand which ones truly didn't have things like formaldehyde in them, because a lot of them do, and they're captured in different ways in the material. The program of the house, I'll run through it pretty quick, just kind of meeting, administration, research, and then there's a lab at the top. I'm going to buzz through the plans pretty quickly, because I think I'm going to go over. I'll get you to the section. It's pretty small. You see the footprint of the house is really only about like 900 square feet per floor. It's pretty tiny. And so the stairwell really is kind of a critical way to control acoustics. We structured all the stairs off of laminated plywood balustrade, which kind of became a sort of partition wall. This is a cross-section that shows the lab up top. We had to open that up to get daylighting all the way through. We got to keep all the old timber. Up here, we used it actually for some of our lateral forces and as a light baffle. And down here, where we were adding concrete on these floors, we had to sister all those joists. And my point before about the issues with the insulation was that we took the house apart basically. We had to get all the engineered lumber back in to reframe it because the office loading was so significant. We actually had to lift it up again to basically get a sill to transfer all the weight down. And then the contractor clad the whole thing in the wood fiber insulation, and it was and it was difficult to get the insulation on site. And once they got it there, they were kind of patting themselves on the back that they had gotten it up. And then we got to site, and the next day was going to rain, and they hadn't thought about that. And so they immediately had to go and essentially bag the house, or else all of that fiber insulation was going to go bad immediately, and it was going to rot. And so that's something that kind of as you go through the process, we actually had to work through that with them. And so that's a kind of tricky part of the replacement strategies. Geothermal on the floors, you can see this. All the wiring in the house is pretty significant. Sections where we kept the lumber, sections where we had to rebuild some of the lumber, and the engineered LVLs throughout the house. And then we kind of got to the finished product. We use untreated cedar on the outsides, so that it required minimal upkeep. You can actually treat it with vinegar over time if it gets a little bit, if it gets any staining on it. We used a kind of carbonized wood for the ramp, which ended up being actually a pretty good cost savings even over concrete, which is what the contractor was actually pushing for. Inside the house, we took out a lot of the walls. We have all these engineered columns. We had to sand them down. These are all the sister joists that we use. There's really just a floor down to the basement, and then one floor above for the staff, and then the labs up top. But you can see the daylight in the house is pretty significant. The daylight even in the stairwell comes through the solar chimney. The workspaces above, all the light that comes in through the skylights isn't lost on the third floor. It kind of comes down. We had to sort of sand out. And so there's a couple of details that are still being finished up. This is that double-layered plywood sort of balustrade partition that supported the whole stair. And these are these kind of lab spaces above, these highly wired office spaces. And then it gets you to the basement where, again, we kind of dug out light wells. We supported them with heavy timber. We made gardens out of the light wells, and we got bigger meeting spaces. This used to be a room with one small window in it, and so we really had to do a lot of work to take that apart and make that possible. So I thought maybe I would end with something that, to me, somehow relates to, of course, wood, but I think it's bigger than that, and I think it's more instructive about how maybe we're a little late on things, but I do think that there's really no other time that we have other than right now to basically start counteracting all the various forces of carbon, all the various forces of emissions, and use things like wood, use wood replacements wherever we can to essentially try our best to right the ship. So anyway, sorry I had to rush through the end, but anyway, thank you very much.
Thank you, Erin. We have promised everyone a quick discussion, so could I have Tahar Masadi, our Professor of Sustainability, Frank Jacobus, Associate Head of Department, Thomas, Kelly, Erin, and Jeremy quickly. And we want to have a few minutes of conversation before we move forward in the evening.
Big first question I have is, Thomas, you mentioned at the beginning this idea that we're at the Prius stage of mass timber, and then Kelly, you had mentioned that Kelly, you had mentioned that the number of these structural issues and things that are being resolved right now or thought about right now with respect to mass timber. So just for each of you, I'd wonder what is like the most pressing issue, the most immediate thing that's coming that we can solve next to get us past the PRIA stage of mass timber.
I guess. You hear me? Yeah. I thought that up like last night, so because I wanted to say something a bit different. But I do kind of believe it. The more I thought about it, it made sense to me. So, and I think it's very different for different parts of the world. So, I think the United States, or you can't really classify North America, I'd say the U.S. market that I'm obviously most familiar with. I think we are kind of, Priuses aren't really popular in Europe, you know, I think, but there's, so what I'm saying is like, I don't think for us to move forward, we need to put out like real examples of how this material can be used in you know, real buildings for, you know, bring it more into the mainstream is what I'm saying. And I think it's going to be a little bit, I would think, of a different equation in the United States than I would say maybe in Europe, because I've worked in both places, and the cultures of building are different. So I think my sense is always to think about the culture and how you can impact the culture and where you're at. So the Prius did a really good job of that here, and I don't think we'd be thinking about driving electric cars if they hadn't come out with the Prius 20 years ago. So that's my sense on it.
Sorry, I'm a bit close. I don't think there's one particular technical issue that we need to all be focusing on. I think the issue is more sharing knowledge, education, and making sure everybody, once we do these projects, you know, we openly talk about the things that went wrong as well as the things that we did right, which is what I tried to do today. And I hope that if everyone who does work in engineered timber does that, then everyone learns the same lessons at the same time rather than repeating the same mistakes. And I think that's an issue that we should address.
I can comment.
Yeah, I'd love it. Yeah, I think that was
going. So, if you apply the same thinking to sustainability, and if we applied it to earthquakes in New Zealand, so the outcome of the earthquakes in New Zealand is that the best corporate practices want to be in a fully earthquake resilient building. You would have the same comment presumably on sustainability, you know, like a factored in thing. And so there's a real opportunity there in actually using the companies that are a success to drive using timber. Yeah. And if you look at the timber buildings in New Zealand being done, they've got the best tenants in them, and that they're therefore trying to attract the best people to work for them, and the fact that they're visibly earthquake resilient is a big part of it.
Yeah.
I mean, it's everything feels like it's kind of beta stage right now, which I think is both exciting and also feels like it's 20 years too late. So it just feels like everybody's got to get going post haste. You can't. The building industry is so complicated that that progress never feels fast. And I think one of the things that I learned from the project that I was just talking about is that the smallest things are hard to get on site in the U.S. And if you're depending on certain kinds of materials, especially like a lot of the wood replacement materials are sort of not that market ready yet. And so we had so many things that got substituted at the last minute, which on a project like that is catastrophe, because you have to go through and recalculate everything on the carbon balance. So I mean, the building industry is really has so much potential, but it's so challenging to get all the different pieces and parts of it working. I mean, it's like, you know, it's a big ship to turn, and everything's got to go at the same time.
Yeah. Well, one of the things that I was thinking about as you all were presenting, just as an educator, was, and Peter had mentioned this briefly, but how do we educate for this sort of world? There's so much to talk about here, and it's a pretty general question, but this idea of knowing the manufacturer. We just visited a mass plywood plant in Oregon, knowing what the rules of manufacturing are, knowing, as you were saying, Jeremy, knowing your local environment and who can do what in your local environment and with what materials. And so it's such a complex array of things, because I'd mentioned 2 out of probably 10 or 15 different things one would have to know. And so what are your thoughts in terms of how we educate for this environment? It might not just be mass timber, but it's the idea of being better builders and being more aware builders. The stuff that you were mentioning, Erin, is just an array of complexity. As you were saying, just the knowledge sets that need to be there and knowing how to tap into them. Do you look back to your architecture educations or structural engineering education and say, okay, here are the things that we need to change? Or do you look back and say, no, this was a fantastic education to deal with wicked problems, and maybe the kind of education we're talking about is a master's study level thing where we're really tapping into manufacturing and other sort of rule sets that we have to have knowledge of in order to be good builders? Loaded question.
It's interesting. I mean, well, I guess I'll just take a first swing at it. I've often thought that, like, the European teaching model, where people graduate with licenses in many countries, is a really productive thing, and I think it gets people out and more ready to deal with the realities of kind of day-to-day life. They have probably more knowledge of even the cross-disciplinary stuff like structural engineering, et cetera, than we do in our country. I mean, we have structural engineering classes, but it's everyone's focused on studio and things like that, and so those things often take a little bit of a back seat. But I think we're playing catch-up in the U.S. as well, because students in other countries where there's more design around them all the time know design a little bit more when they come in. And so we have to spend more time here learning design, and at the expense sometimes of technical and practical things that we have to get in the practice world. So, I mean, I think if I could change one thing, I would create more consistent, like, co-ops, like the way Canadian schools do. No students graduate without a pretty significant little chunk of work experience during the real work year, not during, like, the summers. So they get really embedded in real projects. I mean, things like that are critical, because really it's hard to learn practice in theory. You have to learn it by doing it, and really you need that exposure. I mean, that's the only way around that, I think.
Can I add something to that? So I would say, yes, you need to go and learn what the CLT factory that you went to did, but then you should be empowering students to say, can we do this? I want to do that. I'm going to find out how to do it. Rather than saying, that's what they can do, that's what we're going to do. Because that's not the answer. The answer is to tap into their knowledge and say, but if we did this from left field.
Right,
yeah.
right, yeah.
For me, I don't know if going and visiting, I know you just came to Portland and saw a CLT plant, and the mass timber plant. I don't know if that's really what's needed. I believe you just have to try to instill in students, like, a passion for making an idea real. And if you can even do that at a small scale, like a little thing, you can then learn how to do it at a big scale. And it's not just about making it out of one material, it's about bringing all those materials together to make one thing. And I felt I got to do that when I was an undergrad at Berkeley, but because I kind of just lived in the shop and I had these sort of weird ideas and I just made them. and actually, when I look back, and I went to graduate school at the GSD, and it was a totally different experience, super valuable too. But that kind of connection of an idea to an object that then creates an experience is really fundamental to architecture. So I feel if schools can allow that to happen and students be able to see what the implications of that is. And I think that's the thing I think is new, is this idea that, and I think culinary folks are way more into this than architects. Like, they're thinking about, they get the food and how is it grown and how does that impact the people that grow it, you know, and where does it come from and what are the options? And I think we're sort of still in the TV dinner phase of like, of architecture sometimes, you know, and we're trying to push out of that. And I think a lot of architects are doing that. I just feel that showing students, looking at other models, like the culinary traditions, other artists, you know, that sometimes there's answers in those ways of practice.
Sorry, just add to that. I can't really comment on teaching of architecture in the US, but from my engineering degree, it was a while ago now in the UK. And to be honest, it was a very good degree program, and I wouldn't do it differently. But I think the most I've learned is on the job and actually getting your hands dirty and doing those smaller projects like the one at Burning Man that was talked about earlier. We've done another couple of projects like that where you're actually crowdfunding, fundraising, finding people to help on a charity project, and then you've got to adapt your design to meet that budget, and that is a massive learning curve. But it's also it also really gets you enthusiastic about something, and it's as Thomas just said, it's teaching how to be passionate about what you're doing, and that's rather than just how to do it. I think that's definitely the way forward.
I want to thank you for a very nice presentation, each one of you. And I was also struck by, if you will, the research that went on in trying to understand, if you will, the role of the CLT, whether from an energy standpoint or whether from acoustical response. I don't know whether there was an IAC or an STC in your floor, but certainly it began to give an idea of how that could perform. And then you have a very interesting example. You are now collaborating with Ali Malkawi, and who's just trained as an energy simulation guy, and now suddenly it's merging into the CLT considerations. I think we can see that this, if you will, material is making headways, if you will, into the paradigm shift that has been really engaged through the zero emission building. I think we see that really as a, but I think there is more work that remains, and I feel like the thing that we need is some metrics, if you will, that could help us understand, for instance, the contribution of, let's say, mass timber into the life cycle. That's, for me, that's something we want to do. You were talking about, conversions to zero emission. In what way does, CLT, for instance, become instrumental at reducing, if you will, that, emission? That for me, and then the other thing which really struck me is all the moisture experiments and structural experiments that were engaged, from each one of you. And I'm wondering, is that engaged because there is a need to know better this material? Or is it because there is no standard yet that you can go to a manual and basically say, you know what, I know exactly how hydrometric condition behave into this material. Is that something that really motivated, if you will, these tests?
I think we're kind of jumping ahead with this material, not in a bad way, in a great way, but we're designing way ahead of code.
Yes.
And that's why we're having to do our own testing and our own experiments. And I personally, that's a really exciting part of my job and why I absolutely love it at the moment. But I think we need to be publishing those results and sharing those results and getting to a point where they are codified so everybody can use them.
I mean, I feel like there's two sides to what we've been involved with. One is just the kind of hard-headed, prosaic, they want this test for this material and we have to get it done. Otherwise, we're not going to be able to build this building. And there's a lot of that, you know, just proving in, at least here in the US, that, okay, we've done this test in the United States, which, even though they've done it maybe 4 times in Europe or 5 times in Canada, we have to say that we've done it here in Texas or wherever, you know, Pennsylvania, and here it is, you know, and it passed. And everyone's like, okay, stamp, next, okay, next test. So there's that side of it, which is just purely like operational. You're like, 'cause your building's not gonna happen if you don't have that test or you don't have something equivalent. And then there's, I think, an idea of play, which is, you know, and that's sort of what we try to engage in with, we've done a little bit with mass plywood panels and the Freres company. It's just like, hey, you've got this amazing CNC machine. Let's see if we can, you know, push you to the limit of how you would use it. And in the process, they learn how to use it, and then that enables us to potentially use it at a bigger scale on a building. But I do think I'm always you know, it's like you're not just gonna go out there and run a marathon. You know, you're gonna walk around the block, and then you maybe run a 10K, and then, you know, run a half marathon. So that's why I kind of refer back to the Prius, which is, it's not, it's definitely like the half marathon 10K.
Do you drive a Prius?
I do, actually. My wife bought it. No, I'm joking. No, we bought it. I have a Prius, and, you know, it's kind of a gutless car that gets you from A to B. And maybe it makes us feel a little better about ourselves, you know. But definitely the next car is going to be a fully electric car.
So I kind of agree the same thing here. So there's play, us testing, you know, like testing LVL, making tables, starting on houses. We've only actually got involved in 2 proper tests for each of those buildings I showed. That's because it hadn't been done before. And if we didn't do it, it wasn't going to happen.
No building.
Yeah, yeah. And I wouldn't be able to sleep, right? So testing doesn't happen often.
I was only going to add that, well, what we didn't actually have to, I mean, there were some things we had to do from scratch for House Zero, for instance. Some of the machinery was kind of basically purpose-built for that project based on European, like, more efficient models. But the thing that needed the most testing was we had to essentially change the way the contractor operated on many levels. We had to make sure that they were ordering materials in a different sequence than they normally order them, because there were some things that were such long lead time items that they had never experienced that before. So there were some things that didn't come through on time. So I think that, you know, there's like the sort of fire code legal testing, but then there's also essentially workshopping with the actual builder itself about how to do this differently to make sure that this strange set of requirements that you're giving them that they've never seen before can be done in a way that they can do, that they can pull off. And a lot of those were failures. I mean, we had to change the way we were going to do half the things we were going to do, because they went into normal mode, and we had to keep reminding them, this is not normal, what we're asking you to do.
I just have kind of a completely different question. Because really this event here, and I'm going to a little bit, you know, brings to mind what we call the old Siams, if you are familiar with them. What we call the Congrès International de l'Architecture Moderne, which is basically the Athena Charter at the wake of the Industrial Revolution. Those were momentous meetings that really kind of established the tenets of modern architecture. And today's event, or this long weekend's event, really kind of sets the building blocks maybe for new manifestos about the use and the application of, you know, this mass timber. As we can have seen through all these presentations, I mean, there is a critical mass there that I think it's about time, maybe another round, where we all meet and put into sort of words to paper what exactly we want to see achieved, with this new material. It is somebody, he said that, steel was last century's technology. I think CLT is this century's technology, and I think we need to kind of really think about it as a potential. So my question to you, where do you see, if you will, this, kind of manifesto move forward, if we were to speak about the CLT I understand the umbrella of sustainability, but for a community that is architects, designers, engineers that are interested in, engaging this material, how do you see the next 10, 20 years?
Can I prompt
Yes,
back the other way?
Sure.
I don't think we've ever done a CLT wall that's been lined over with something. And if you have to do a CLT wall and then you're lining it and you're cladding it, there's nothing cheaper than a frame wall. In which case, why do the CLT unless it's got a massive sustainable issue? But you can't get that past your builder. And you can't generally stand there and explain to a client that you're going to spend X times more than you just can with something that they make every day. So there's a point about quality of architecture at the end of that if you're going to do the CLT wall and you're going to express it, you make a really good building.
I would, I'm really wary of manifestos, to be honest with you. So that word kind of frightens me. I think there's a different path in my view, and I've worked in a lot of places, and what has been really fascinating to me is like by solving your sort of regional problems as best you can within the sort of constraints of that particular environment, and in Oregon, we've got a lot of wood, so it makes sense, to sort of work with that material. And by focusing very specifically on those issues, you might come up with solutions that have global worth. You don't know if they will or not. Those things. And so I feel like maybe by solving the problems that are right in front of your face, and opening your eyes to what's actually really happening, then whether it's a small project or a big project, I do feel like you can have a global impact, and I think that's different than like, I think there was this time where you're like, oh, let's do something. It's like we're going to do the international style. It's like we're going to put the same building here and the same building there, and then and part of that is led to where we are today, where everything's a glass box, or there's sort of this sort of way people think about quote modernism. So I guess I'm not saying that there shouldn't be like a document or kind of a record, but I think it's really to think about where you're at and how you deal with those issues in that place.
Let's take one question from the audience here, and there's only going to be one question I think allowed from we're running out of time. So who has one question from the? Yeah, we got right here. You got your hand up first. So. Where were you at age 3? What were you doing?
I can't help but ask, what do you suggest for students who are looking at graduation in the next couple of years, who are about to step out into the practicing world, that want to be a part of the solution? Because that seems to be a relatively small section currently of the world.
Then you just go and start trying to solve it. You ask the question, I want to try and solve it. Where do I want to go and do that? Seriously.
Keep trying.
You don't ask the question, you don't solve.
I think there's a real opportunity. I mean, with the whole Architects and Engineers Declare that we've been doing in London and the UK over the last month, it's started to change our mindsets. And it'd be great if all students coming forward adopt that straight away. And when you're asking that question at the beginning of every design decision, is what's the impact of this? What's the carbon spent? Getting to grips with the amount of carbon in it, and there are life cycle values of carbon for each material out there. It changes depending on what part of the world you're in. But if you get the right numbers, it's very easy to work out the volume of material you're using for a certain building and see how much carbon you're using and compare the carbon in the options as well as the cost or the aesthetics or anything else. And having that ingrained in you from the very start of your career is, I think, a massive benefit to the industry for the next generation of designers coming through.
I would maybe suggest that you do a little bit of assessment on your own part, where you say, what's my perspective on the greatest problems that we're going to have to solve in the next 20 or 30 years? They were different 20 years ago. When I came out of school, people were really just focused on what's the most progressive, amazing design you can create for whatever program you're given. That seems kind of silly now. I mean, that's sort of important, I guess, but it's a nice byproduct. But I think that the real product has to be something that's actually, for lack of a less ideal way of saying it, it's something that's got to try to save the world a little bit at a time, each time you design something. So I would say, try to analyze the problem from your perspective, see what you think is out there, try to align it with something that you personally are invested in, because you're never going to be inventive unless you're in love with the problem you're solving. And then either do it yourself, try to find a way to do it yourself, or go somewhere and work with an office or a place that's trying to solve problems in the same way.
Just keep it short. I mean, there's somebody said something about, don't let a crisis go unwasted or something to that degree. It's like there's some big problems out there. Just go at it. I can't say more than that.
Thank you. Thank you all. Appreciate it.
I want to thank Professors Masadi and Jacobus for their questions and the issues raised, and we'll return to them in a more general way tomorrow. I want to thank this afternoon's presenters and ask for a round of applause for everyone. Thank you. And you are excused from the stage. We do look ahead not only to a few events this evening, which I'll come to quickly, but to touch on tomorrow morning in particular. Earlier, or on the schedule, it says that we will convene here at 10 o'clock for coffee, 10:30 till noon for a seminar, which is intended to be synthetic, integrative, and not just a rehashing of the points of view which we've gone through over the last day and a half. Susan Jones, who is as well known for her research, her advocacy, as much as for her work in this field, has joyfully joined us to serve as tomorrow's moderator. And in order to set us thinking ahead of time, I've asked Susan to just say a few words of preview for tomorrow's morning session. Susan.
Thank you very much, Peter, and thank you to all of you. I think I had the best job in the house. I just got to sit and listen to my incredibly talented peers about all the amazing work you're doing internationally, and I felt really lucky. I took about 20 pages of notes, so I feel much more smarter than I did in the beginning. But for tomorrow, I don't know if a seminar is the right word or if it's more about being synthetic and being reflective. On the other hand, these panels have been incredibly reflective and synthetic. So what I actually thought, and I just sprung this on Peter about 5 minutes ago, I've been thinking about it all day, is that actually we take that question. we take that question that you said, what do we do now? What does the student population, what does the group of talent in this room do now? Well, we have something in front of us right now that's much more immediate and much more right in front of us, and that's a brief that Peter MacKeith and the dean and the school and Anthony Timberland has allowed us to think, to dream, to envision, to write, to imagine the best sort of brief for the Anthony Timberland Center for the Design and Material Innovation located here at the University of Arkansas. It's an upcoming project which is very much on the minds of University of Arkansas here. And to meet the challenge of what we decided here, what we talked about here for 24 hours solid, it feels like more, is that there is a huge and wonderful, unique opportunity here. Harvard's answer, thank you, Erin, for that excellent explanation of that project, was to take a, 2,700 square foot house next to Somerville, 1940s, and make it into a net zero project. That was Harvard's answer to that. What's the University of Arkansas's answer to that question? So I would like to use that just as a model, not to necessarily think about it as, we're going to design this, please nobody charrettes tonight, please no designs. We'll have a couple of students take a lot of notes so it actually can be a useful document. Because the one thing I've sat through for so many conferences, and like this, great conferences, you come out high and on top of the world, and you go back to your desk the next day and you say, God, I got to get this detail out to the contractor tomorrow, and this fades away. So let's have a living document. Let's create something tomorrow as a dialogue among all of us at the table with students, with faculty. I look forward to discussing further at 10:30 tomorrow. Thank you, Peter.
Thank you, Susan. Really, I think it could just be the 15 of us or 20 of us sort of have been most engaged in the planning and presenting of this conference, but I very much hope to see many of you and your friends and classmates and colleagues in the larger circle out in the Smith Gallery, because I think you're right. The time to act is now. That is what I have been trying to tell this school for at least 5 years. It is time to act, and we have the means to do so now, and we certainly have the critical mass of intellectual and creative minds with us this weekend to act, to help us determine how best to move forward. So please, the call is out. Pass the word along to classmates and colleagues alike that we'll have that discussion tomorrow. Ahead of that, I just want to make a few further notes. We've got a reception, food and drink downstairs around the Time for Timber exhibition. Following that at 6:30, as I think has been advertised already, we will have a special session in the Young Gallery, this upper floor gallery, Voices of Practice, Women, Architecture, Engineering. And we are taking advantage of the sheer fact of intellectual and creative strength that is part of our overall presenters group this weekend, with Andrea Lears, Susan Jones, Natalie Telewiak, Kelly Harrison, and Tanya Luthi with us, as well as other members of the Arkansas professional community, other members of the architecture and engineering student cohorts across the campus. That will be set in motion by Associate Dean Ethel Goodstein-Murphy, among others, and that will convene at 6:30 in the gallery. There'll be more food and drink there to keep that conversation going until 7:45 or so. I very much hope that you can attend that, stay in there for that. Besides that, Steve Luoni, who's director of our Community Design Center, has generously offered to open the doors to the Community Design Center at the Pryor Center on the downtown square, roughly 7:30 to 8:15 or so, to show people the good work of the CDC. So there's a number of events, and I bid you welcome to all of them. These are, again, it's a remarkable time in the school of such accomplishment, and it's a privilege to be able to be part of it and to shepherd this entire effort along. You will forgive me if I need to conclude not only by thanking everyone, but by going one step further with yet another of our sponsors. As you depart, at least upstairs, you'll see a table filled with these, what I call artisanal blocks of Arkansas cross-laminated timber, made in our own shops of Arkansas Southern Yellow Pine. And they are embossed on the one side with the University of Arkansas Fay Jones School of Architecture insignia, and on the other side with that of our other sponsor, Walmart. It is, I think, by now well known that Walmart intends to construct its corporate campus of 3 million structured square feet, predominantly out of mass timber. And the effects that will have upon the CLT production industry remain to be seen, especially here in Arkansas, but I think I can say they will be seen and felt, and certainly the effect that they will have upon the North American market simply in this commitment that they are making will be significant. So we have much to be looking forward to in that regard. But all of that is merely to lead me to express my thanks and gratitude to those who've presented yesterday, this morning, this afternoon, those who will be moderating this evening and tomorrow, those who moderated our panels, members of our great faculty who have assisted in this, and wish you well for both the reception to come, the evening to come, and I look forward to seeing you here tomorrow as we begin to plan for the future. Thank you again on behalf of the Fay Jones School and the University of Arkansas. See you soon with a glass of a good beverage around the exhibition. Thank you.